The universe, it's vast, puzzling, and at times overwhelmingly mysterious. Its beauty and scale transcend our ability to truly comprehend them. From the endless stretch of space to the stars and planets scattered across its infinite expanse, the cosmos is not just a backdrop to our existence, it is the very source of everything we know. The universe is where life began, a vast arena of creation, destruction, and rebirth. Yet, despite our insatiable curiosity, it remains filled with unanswered questions and perplexing phenomena that continue to challenge even the most brilliant minds. In this exploration, we will venture into one of the most enduring questions of all. What lies beyond everything we can observe? To help visualize the immensity of this question, imagine standing at the edge of a vast ocean, an ocean that stretches endlessly, far beyond the limits of human vision. Now, picture that each drop of water in this ocean represents a single star. This gives a glimpse of just how immense our universe truly is. Within our own galaxy, the Milky Way, there are at least 100 billion stars. But that's only one galaxy. If we expand our view to the visible universe, we find a staggering estimate of around 2 trillion galaxies, both large and small. And when we multiply the number of stars in each of these galaxies by that immense figure, we arrive at a number almost beyond human comprehension, roughly 200 billion trillion stars. Take a moment to grasp the enormity of that number, a number so vast it's hard to fully appreciate. But that's just the stars. Scientists now know that most stars have planets orbiting them, and many of those planets could resemble Earth. With such an unfathomably large number of planets out there, the question arises, are we truly alone in the universe? Despite the immense possibilities, some still claim with certainty that we are the only intelligent life in existence. But can such a belief really be justified? Among the thousands of exoplanets discovered so far, many share characteristics that suggest they might be capable of supporting life. With such a massive number of planets, it seems nearly impossible that none of them could harbor life. Yet something may be preventing us from knowing the truth. Could it be that the answer is already out there, hiding just beyond our reach? Today, we will dive deep into this cosmic mystery. Hold on to your seat, because what you're about to learn may both amaze and unsettle you. We will explore theories suggesting that discovering fossils of complex life on another planet might actually be terrifying news. We'll also delve into ideas that propose we might be living inside a massive simulation, or even within a cosmic nature reserve. Keep watching, because the answers to these questions might just change the way you see the universe forever. The seeds of this inquiry were planted back in 1950 during a seemingly casual lunchtime conversation. A group of renowned physicists, including Enrico Fermi, an American scientist of Italian descent, were gathered at a university. Among them were notable figures like Emil Kopinski, Edward Teller, and Herbert York. Their discussion, which had initially focused on reports of unidentified flying objects, a topic making headlines at the time, soon took a turn. The conversation shifted to a much broader yet equally profound question. Could physical objects ever travel faster than the speed of light? Then, Fermi, ever the thoughtful scientist, posed a simple but groundbreaking question. Where is everybody? He was referring to extraterrestrial civilizations. If the universe is as vast as it seems, filled with stars and planets, why haven't we seen any clear signs of intelligent life? Why haven't aliens reached out to us? By 1950, humanity had been broadcasting radio and television signals into space for over 100 years. In addition, scientists had sent deliberate messages into the cosmos, hoping to make contact with intelligent extraterrestrials. Thousands of people worldwide had joined efforts like the SETI, Search for Extraterrestrial Intelligence program, analyzing signals from space. Yet despite these efforts, all we had received in return was silence. Fermi's curiosity led him to approach the question mathematically. He started multiplying probabilities, the chances of stars having planets, the likelihood of life forming, the chances of intelligent civilizations developing, and so on. Based on his rough calculations, alien civilizations should have visited Earth long ago. Many times, in fact. So why hadn't they? Fermi proposed several possible explanations. Perhaps interstellar travel is simply impossible. Maybe it's technically feasible, but the effort required is not worth it. Or perhaps civilizations don't last long enough to make contact. But there's something else Fermi didn't know about at the time: wormholes. These are hypothetical shortcuts through space-time. Had he known, he might have jokingly suggested that every home on Earth already had a hidden wormhole, with an alien observing us from the other side. Could it be that we are being watched right now, without even realizing it? Could advanced extraterrestrials be keeping their presence hidden from us? Today, some scientists seriously consider the possibility that wormholes might exist. If we advance our technology just a little more, we may even learn how to create them ourselves. But the question remains: where is everybody? A decade after Fermi's famous question, an astronomer named Frank Drake introduced a tool to explore this very mystery. In 1961, Drake presented the equation that would later bear his name, the Drake equation. This mathematical formula was designed to estimate the number of extraterrestrial civilizations in our galaxy that might be capable of communicating with humanity. It takes multiple factors into account: how often stars are formed, how many of those stars have planets, how many of those planets can support life, how many planets develop intelligent life, and how many of these civilizations are advanced enough to send signals into space. Of course, most of the factors in this equation remain unknown, but that wasn't Drake's point. He didn't create the equation to solve the mystery. He created it to keep the conversation alive, and it worked. For over 70 years, scientists, philosophers, and enthusiasts have debated the implications of Fermi's paradox and the eerie silence of the universe. And we still find ourselves asking the same fundamental question: where is everybody? One of the most widely debated theories about why we haven't found intelligent alien life is called the Great Filter. This theory, introduced by Robin D. Hanson, a researcher at Oxford University's Future of Humanity Institute, suggests that there is an almost insurmountable barrier, either in our past or in our future, that prevents civilizations from advancing beyond a certain point. To put it simply, if human evolution up to this point has been relatively easy, the most difficult and dangerous challenges may still be ahead. At first, this concept might not seem obvious, but let's consider an analogy. Have you ever heard the joke, "I intend to live forever, so far so good"? It's funny when applied to an individual, but it becomes far less amusing when applied to humanity as a whole. Hansen questioned why, despite the high probability of advanced alien civilizations existing, we haven't seen any signs of them. His theory proposed that there may be an unknown factor that makes it incredibly difficult for life to evolve to a point where it can leave a noticeable mark on the universe. Think of this like ripples in a pond. If you throw a small stone into the water every now and then, the ripples will disappear quickly before they have a chance to meet. Now, imagine space as an enormous pond stretching across billions of light years and spanning billions of years. One civilization may just be discovering fire, while another, far across the galaxy, has already self-destructed in a nuclear war. The odds of two civilizations existing at the same time and in the same area are incredibly low. To illustrate this, think about human history. How many times have we been on the brink of destruction? We don't even have to look far back. Take the year 2020, when the global pandemic revealed just how fragile our civilization truly is. Hansen outlined 9 major steps that any civilization must go through to reach an advanced stage of space exploration. From the formation of a solar system with planets capable of supporting life, to the rise of intelligent beings capable of using tools, each step becomes more and more difficult. According to the Great Filter hypothesis, at least one of these steps is nearly impossible to achieve. If the first 8 steps were easy, we would expect to see countless other civilizations at our level of advancement. But we don't. This suggests that the most difficult step, the ability to expand into space, might be the hardest to achieve. If this is the case, then something may be preventing civilizations from surviving long enough to take that final step. What could that something be? It could be nuclear war, a deadly epidemic, a catastrophic asteroid impact, or the collapse of natural resources. Or it could be something we don't yet fully understand. The reality is, the Great Filter might still be ahead of us. Now, let's imagine that we found definitive proof of life on a nearby planet. At first, this might seem like an incredible discovery. If life can emerge on Earth and another planet, surely it must be common throughout the universe, right? But what if we only found simple bacteria on Mars or beneath the icy surface of Europa, Jupiter's moon? That would suggest that the Great Filter occurs after life begins, meaning that the greatest challenges still lie ahead of us. Imagine, however, that we discovered fossils of complex alien life, perhaps even creatures like fish or larger animals. This would be an astonishing discovery, but also a terrifying one. It would imply that life easily reaches the multicellular stage, but rarely survives long enough to become an advanced civilization. In this scenario, the Great Filter would almost certainly lie in humanity's future. As philosopher Nick Bostrom once put it, that would be the worst news ever to make the headlines. Why? Because it would mean that life may be common, but no civilization has ever survived long enough to become interstellar. And if that's the case, why should we believe we'll be the first? Let's take this even further. What if we began discovering alien fossils scattered across the universe? This would be an exhilarating discovery at first, but then something strange happens. We realize there are no signs of intelligent civilizations, no spacecraft, no signals, just the ruins of extinct life. This would suggest that something has wiped out every civilization before they could reach the stars. And if that's true, what are the chances we can avoid the same fate? Before we panic, though, let's remember, this is all still just a theory. Humans have long demonstrated resilience, creativity, and an uncanny ability to solve seemingly impossible problems. There are many alternative explanations for why we haven't found aliens yet, some of them logical, others more bizarre. But all of them remind us of one thing: the universe is still full of mysteries, waiting to be unraveled. To truly understand some of the most strange and bizarre ideas about the universe, we must be willing to set aside our preconceived notions. After all, what we call common sense is often just a set of beliefs shaped by the time and society in which we live. What seems logical today might have seemed absurd centuries ago. Take the story of Giordano Bruno, an Italian philosopher from the 16th century. Bruno dared to suggest that the universe was infinite and that countless other worlds existed beyond our own. His ideas were considered so dangerous that he was executed for them. At the time, the people who condemned him believed they were acting rationally. This serves as a powerful reminder that our boundaries of common sense are constantly shifting. And with that in mind, we will now turn our attention to some of the most extraordinary and possibly transformative ideas about the universe. Ideas that, although they may seem strange now, could one day reshape the way we view everything. One of the most mind-stirring ideas about why we have yet to encounter extraterrestrial life comes from Liu Cixin, a well-known Chinese science fiction author. He introduced the concept of the dark forest hypothesis as an explanation for the Fermi paradox, the contradiction between the high likelihood of extraterrestrial life and the complete lack of evidence for it. According to this theory, the universe operates under a harsh survival rule, much like the natural world on Earth. In this framework, civilizations that reach a level of advancement capable of exploring space quickly realize that broadcasting their existence could be an immensely dangerous decision. Imagine for a moment a dense, dark forest. In this environment, every creature is both a hunter and prey, with survival depending on stealth and secrecy. If a civilization broadcasts its presence to the cosmos, like a lost traveler yelling into a predator-filled jungle, it could quickly attract the attention of more powerful, hostile civilizations, thus risking immediate annihilation before even realizing the impending danger. In essence, civilizations must remain silent to survive, just as creatures in a dark forest must avoid revealing their locations to predators. This idea echoes a warning issued by the legendary physicist Stephen Hawking, who also cautioned against sending signals into deep space. He feared that should an advanced extraterrestrial civilization detect our presence, the consequences could be catastrophic. Hawking likened the potential fallout to the arrival of European explorers in the Americas, a historic encounter that led to the devastating destruction of indigenous civilizations. However, what if Hawking's warning is only partially accurate? What if intelligent extraterrestrials have already discovered us, but have chosen to observe rather than interact? This brings us to a fascinating possibility that Earth, or perhaps even the entire galaxy, might be part of an intergalactic nature reserve, protected, shielded, and off-limits to advanced civilizations. To grasp this concept, consider the Serengeti National Park in Tanzania, one of the most famous wildlife reserves in the world. Spanning almost 15,000 square kilometers, it is home to over 3 million large animals and nearly 500 species of birds. Every year, thousands of tourists visit to witness the majestic wildlife. Yet, most of the animals within the park are blissfully unaware of the human presence around them. They go about their lives, oblivious to the fact that their world is carefully managed by beings far beyond their comprehension. Now, imagine a parallel scenario for humanity. What if we are like those animals living in a cosmic Serengeti? An advanced alien species, perhaps millennia ahead of us, might have placed us here, carefully monitoring our development while enforcing certain boundaries to prevent direct contact. They remain invisible, operating from a distance, much like how a wildebeest or zebra would be unaware of the intricacies of human civilization. If this hypothesis holds any truth, then when we wonder, where is everybody? The answer might be that we simply lack the perception to detect them. What if, in the grand scheme of things, we are as insignificant to these advanced extraterrestrials as ants or butterflies are to us? Consider this analogy. When an ant scurries across the ground, it has no understanding of the vast human world around it. Skyscrapers, airplanes, the internet, or even our social structures. Similarly, a species that is thousands or even millions of years more advanced than us might exist in ways that are utterly beyond our comprehension. To them, we may be no more significant than the ants beneath our feet, and the idea of interacting with us might not even be worth their attention. This idea of humanity being entirely irrelevant to advanced extraterrestrials is a humbling thought, but it is not the most mind-bending possibility that researchers have proposed. The next theory pushes the boundaries even further. Nick Bostrom, a Swedish philosopher and professor at Oxford University, put forward one of the most mind-altering ideas in the realm of extraterrestrial life, the simulation hypothesis. Published in 2003, Bostrom's theory suggests that if a civilization reaches a certain level of technological advancement, it will likely develop computers powerful enough to create simulations that are indistinguishable from reality. These simulations could be so sophisticated that the beings inside them, like us, would be completely unaware they are not living in the real world. To help conceptualize this, think about the evolution of video games. The earliest computer games were simple and pixelated, but today's video games feature photorealistic environments and lifelike characters. As technology continues to advance, it is not unreasonable to imagine that in the future, we will be able to create virtual worlds so real that they are indistinguishable from our own. Now, consider this scenario on a larger scale. What if we, in fact, are already living inside one of these simulations? If every advanced civilization eventually creates such virtual worlds, the number of simulated beings could easily surpass those in the base reality. This raises a profound question. What if the odds of us living in a simulation are higher than the odds of us existing in what we think of as the real universe? If this simulation hypothesis were true, the reason we do not encounter intelligent alien civilizations might be simple. They are not part of the simulation at all, or perhaps they exist in a different layer of the simulation beyond our access. While this idea is fascinating, it takes us into a realm of speculation that is both mind-bending and unsettling. But perhaps there is an even more disquieting explanation, one that is far simpler and more terrifying than any simulation or intergalactic nature reserve. What if the reason we do not hear from other civilizations is that there are no others? What if we are the only intelligent life in the universe? This thought is perhaps the most chilling answer to the Fermi paradox. It eliminates all hope of discovering other intelligent beings and forces us to face the terrifying possibility that the future of intelligence in the cosmos rests solely on our shoulders. There is no older, wiser civilization to guide us, no one to help us navigate the dangers we face as a species. If we destroy ourselves, no one will be there to pick up the pieces. This realization transforms the silence of the universe from an eerie mystery into a profoundly unsettling truth. If we are truly alone, every decision we make about the future of our planet, our technology, and our survival takes on a far greater weight. The responsibility for the fate of intelligent life in the universe would rest solely with us, making each moment in human history crucial, and the stakes unimaginably high. The vastness of the universe has always been a source of wonder and speculation. One of the most intriguing and unsettling theories about the cosmos and our place in it is the dark forest hypothesis. This theory, introduced by Chinese science fiction writer Liu Cixin, offers an explanation for one of the greatest paradoxes in modern science, the Fermi paradox. This paradox is the apparent contradiction between the high probability that alien civilizations exist and the complete lack of evidence to support that belief. The dark forest hypothesis suggests that intelligent life in the universe is engaged in an endless, deadly struggle for survival, much like the predators and prey in the natural world. In such a universe, civilizations must compete for resources, and only the most powerful can thrive. The theory posits that any civilization that reaches a certain level of technological development will likely go to great lengths to conceal its existence, fearing that exposure could lead to its destruction. Imagine a lone traveler walking through a dense forest on a dark night. The forest may seem empty, silent, and calm, but hidden in the shadows, predators are watching. If the traveler makes too much noise or takes a wrong step, they will reveal their presence, and before they even realize what's happening, they could be gone. This is the essence of the dark forest theory. Civilizations that make themselves known to the cosmos could be like that unlucky traveler, unaware of the danger they've just invited. This notion resonates with the concerns of some of the most renowned scientists in the world. One of the most famous voices of caution was physicist Stephen Hawking. He warned that broadcasting signals into space in hopes of attracting the attention of extraterrestrial civilizations might not be the wisest idea. If a highly advanced civilization were to detect our signals, the response could be far from friendly. History itself provides a grim reminder of the consequences of such contact. When European explorers arrived in the Americas, they brought with them technology and weapons that overwhelmed and ultimately led to the destruction of many native civilizations. If such a pattern were to play out on an intergalactic scale, Earth could face a similar fate. The implications of this are deeply unsettling. Could it be that intelligent extraterrestrials already know of our existence and are simply choosing to watch us from a distance, perhaps silently awaiting our inevitable self-destruction? To explore this possibility further, consider the Serengeti National Park in Tanzania. Spanning nearly 15,000 square kilometers, it is one of the most biodiverse and teeming ecosystems on Earth. Home to millions of large animals and nearly 500 species of birds, it sees vast migrations of wildebeests, gazelles, and zebras each year, traveling thousands of kilometers in search of food and water. Despite the fact that the Serengeti is one of the most visited wildlife reserves in the world, many of the animals that live there have never encountered a human being. Even fewer are aware of the human presence that established the park and its boundaries. To the animals in the Serengeti, humans are an invisible force, like gods shaping the world around them. The animals have no understanding of the boundaries that define the park, the laws that protect their habitats, or the role humans play in their conservation. What if, in a similar vein, we are nothing more than inhabitants of a cosmic nature reserve? Could it be that our entire planet, and perhaps even our universe, is carefully curated by an advanced civilization that maintains it without ever interacting with us directly? To these advanced beings, we might be no more significant than ants or butterflies are to us. Just as an ant might wonder why it never encounters larger creatures that govern its world, we might never fully understand the forces that shape our existence. We are too small, too limited in our perspective to comprehend the larger reality that surrounds us. Now, consider an even more mind-bending possibility. What if we are living in a simulation? The simulation hypothesis, one of the most controversial and thought-provoking ideas in modern philosophy and science, was introduced by Swedish philosopher Nick Bostrom in 2003. Bostrom proposed that as humanity's technological capabilities grow, future generations will likely create highly sophisticated simulations of the past. These simulations could be so advanced that the beings inside them would be unable to tell that their reality is artificial. This raises a profoundly unsettling question. What if we are already living in such a simulation? Take a moment to consider the rapid pace of advancement in video game technology. Each year, video games become more immersive, more realistic, and more intricate. If this trend continues, it's not far-fetched to imagine a future where simulations are so lifelike that the inhabitants wouldn't even realize they are inside a computer-generated world. If that's possible, then it might be even more likely that we are living inside one of those simulations right now, rather than in the real universe. This could mean that the vast emptiness of space, the so-called Great Silence that scientists have long struggled to explain, might not be an inherent feature of the universe at all. Instead, it could simply be a limitation of the simulation we are trapped in, like the boundaries of a video game. The stars, galaxies, and entire cosmos might be nothing more than a programmed illusion designed to give the appearance of a vast, mysterious universe. While these ideas are certainly speculative and in many cases highly controversial, they bring attention to one of the most perplexing and chilling possibilities, that we might truly be alone in the universe. The Fermi paradox raises a question that has intrigued scientists for decades. If life is so common in the universe, why have we found no evidence of extraterrestrial civilizations? One of the more unsettling answers is that perhaps there are no other intelligent beings out there at all. If this is the case, then all our dreams of discovering alien life might be nothing more than wishful thinking. Many scientists, including the famous Carl Sagan and Frank Drake, have dedicated their lives to the search for extraterrestrial intelligence. They believe that Earth is just one of countless planets orbiting ordinary stars in vast, unremarkable galaxies. Yet, despite all our efforts, the silence persists. If life were as common as we expect, surely we would have found evidence of it by now. This leads to the most terrifying possibility of all, that humanity might be the first and possibly the last intelligent species to ever exist in the universe. For much of modern history, scientists adhered to what's known as the mediocrity principle. This idea suggests that Earth and humanity are nothing special, that we are just another planet orbiting an average star in a universe filled with countless other worlds, many of which should also harbor life. If this were true, then we should have already found signs of alien civilizations. Yet, the silence remains deafening. The mediocrity principle was once a comforting idea, an optimistic belief that life in the universe was common, and that we were just one part of a much larger, bustling cosmic community. For many years, it was rarely questioned. But now, faced with the vast emptiness around us, it seems that the principle may have been too simplistic. Perhaps, instead of being one among many, humanity is truly alone in a universe that, despite its immensity, remains eerily silent. However, as new discoveries were made, doubts started to creep in. If Earth and life itself were so ordinary, then why hadn't we encountered signs of aliens? The more we studied our own planet and its history, the more we began to understand just how many rare and extraordinary conditions had to come together for complex life to not only emerge, but also survive. This led to a disquieting realization, one that would soon gain traction. Life, particularly intelligent life, might be extraordinarily rare in the universe. This theory, which came to be known as the rare Earth hypothesis, proposes that Earth's ability to support life might be far from a cosmic norm. In fact, it suggests that Earth could be one of the very few, if not the only, planets to have ever developed complex life. If this theory proves true, it paints a chilling picture, one where we are almost completely alone in a vast and seemingly infinite universe. It means that the emergence of intelligent life could be an unimaginably rare accident, a one-time miracle that may never repeat anywhere else. For many, this realization is deeply unsettling, even terrifying. The notion that we might be isolated, a cosmic anomaly in an ocean of stars and galaxies, challenges everything we thought we knew about our place in the universe. This unsettling idea was explored in depth by scientists Peter D. Ward and Donald Brownlee in their groundbreaking book, Rare Earth: Why Complex Life is Uncommon in the Universe. In it, they argue that intelligent life can only exist under a very specific set of conditions. Conditions that are so rare that even small variations could prevent life from emerging at all. Most people are familiar with the concept of the Goldilocks zone, the habitable region around a star where conditions are just right for liquid water to exist, neither too hot nor too cold. For a long time, many assumed that if a planet were located in this zone, life was practically guaranteed. But in reality, the situation is far more complicated than that. Earth's ability to support life isn't simply a result of its perfect distance from the sun. There are additional factors, such as our planet's nearly perfect orbit. Unlike many planets with elliptical orbits, Earth's orbit is almost circular. This stability ensures that our planet maintains a relatively constant distance from the sun, preventing drastic seasonal fluctuations that could make survival difficult for life forms. If Earth's orbit were more elongated, we would experience extreme seasonal changes, hotter summers and colder winters, potentially rendering life unsustainable. But that is just the beginning. Even if a planet happens to sit comfortably within the Goldilocks zone, there are countless other conditions that must align in a precise manner for complex life to flourish. Shockingly, it turns out that even the entire galaxy has its own habitable zone, and Earth happens to sit in the perfect spot. The Milky Way is a vast and perilous place, filled with dangers that could easily snuff out life on any planet. For instance, our solar system takes about 235 million years to complete one full orbit around the center of the galaxy. Since the first oceans appeared on Earth, our planet has completed this journey roughly 17 times. Over the course of this journey, we've passed through regions of the galaxy that could have been disastrous for life as we know it. Our solar system has encountered many cosmic threats along the way. One of the most significant of these threats is our location in the Milky Way. While many parts of the galaxy may seem serene, much of it is in what could be described as a dead zone, where conditions for complex life simply do not exist. The closer a star is to the center of the galaxy, the more dangerous it becomes. The center of the Milky Way is home to a supermassive black hole, which churns out intense radiation. This radiation, along with other deadly phenomena like neutron stars and gamma-ray bursts, could potentially sterilize entire planets, eliminating any chance of life. Supernova explosions, the deaths of massive stars, are another critical risk. These events release enormous amounts of energy, enough to devastate everything within several light years. A planet too close to a supernova might have its atmosphere stripped away, making life completely impossible. Even gravitational forces pose a threat. The central regions of the galaxy exert such strong gravitational forces that stars passing through could disrupt a planet's orbit, throwing it out of the habitable zone, or, in extreme cases, ejecting it from its solar system entirely. But it's not just the proximity to the galactic center that presents a risk. The outer reaches of the Milky Way have their own set of problems. Stars located far from the center have a lower concentration of heavy elements, materials essential for forming planets like Earth. Without these elements, planets might still form, but they would be barren, lifeless rocks, devoid of the conditions necessary for life to take hold. Recent studies suggest that the galactic habitable zone, the region where conditions are just right for life, stretches between 7,000 and 9,000 parsecs from the galactic center, about 22,800 to 29,300 light years away. Shockingly, only about 10% of all stars in the Milky Way reside in this narrow, life-sustaining band. And even among these stars, only a small fraction will have planets that are capable of supporting complex life. Earth, in contrast, is located in the sweet spot. Not only does our solar system sit in the galactic habitable zone, but it also follows a nearly perfect circular orbit around the center of the Milky Way. This orbital stability has kept our solar system in an ideal location for billions of years, preventing us from drifting too close to the dangers at the galactic center or too far into the barren outskirts. But even beyond our solar system's location, the entire structure of the Milky Way is remarkable. For an extraordinarily long period, about 10 billion years, the Milky Way has remained largely undisturbed, with no major collisions with other galaxies. This stability has played a key role in allowing life on Earth to develop. In contrast, most galaxies experience frequent collisions, which can disrupt star systems and destroy the delicate balance required for life. This level of galactic stability is incredibly rare. The universe is roughly 13 billion years old, and for about 10 billion years of that time, the Milky Way has avoided major collisions. Only about 7% of galaxies across the universe have experienced this kind of long-term stability. But this peaceful period won't last forever. The Milky Way is currently on a collision course with its closest neighbor, the Andromeda Galaxy. In about 4 billion years, the two galaxies will collide, an event that could disrupt star systems and potentially obliterate any remaining civilizations. If humanity is still around by then, we will face a difficult choice: either become an interstellar civilization capable of surviving beyond the Milky Way, or risk being swept away in the chaos of the galactic merger. If we fail to expand into space in the next few billion years, we may face extinction. When you consider all of these factors, habitable zones, rare conditions, and the exceptional stability of our galaxy, it becomes clear why we have yet to encounter alien life. It's not that life is common, and we simply haven't looked hard enough. It may be that life, especially intelligent life, is so incredibly rare that it barely exists at all. This realization is both humbling and terrifying. If the rare earth hypothesis holds true, we may indeed be one of the only intelligent species in the universe. The responsibility of preserving and expanding life beyond Earth could very well fall entirely on our shoulders. This idea represents a stark departure from the mediocrity principle, which once suggested that life must be ubiquitous in the cosmos. The evidence, however, now appears to tell a different story. We are not just another planet. We are an extraordinary exception in a universe that might be far emptier and more inhospitable than we ever imagined. When we gaze up at the night sky, it's easy to get lost in the shimmering dots of light scattered across the cosmos. We often assume that many of these stars are similar to our sun, varying only in size and brightness. But in truth, the majority of stars in the Milky Way are not solitary like our sun. Instead, they exist in binary or even multiple star systems. Take, for instance, Polaris, the North Star. Most people imagine it as a lone, brilliant point of light. However, in reality, it is part of a complex three-star system, with each star exerting gravitational influence over the others in a dynamic and unpredictable dance. This scenario is often romanticized in science fiction, where alien worlds with two or more suns are depicted in mesmerizing landscapes. The idea of watching 2 or 3 suns set over an alien horizon is captivating, but it's not a scenario that would be conducive to the development of life. Planets in binary or multiple star systems face significant challenges when it comes to maintaining a stable orbit in the habitable zone, the region around a star where conditions allow for liquid water to exist. In a universe filled with countless stars, one might imagine the vast expanse of space as a place teeming with life, where planets orbit stars in harmonious, predictable patterns. However, the reality of such a universe is far more complex, especially when we consider systems with multiple stars. In these systems, the gravitational influence of each star creates a chaotic environment for any planet attempting to maintain a stable orbit. The gravitational tug-of-war between these stars disrupts the delicate balance needed for life to thrive. Planets in such systems experience wild fluctuations in their orbits, leading to unpredictable temperature swings and constant climate shifts. Far from a steady, nurturing environment, these planets become inhospitable, rendering them unsuitable for life as we know it. Yet, we don't need to look to the farthest corners of the galaxy, where multiple stars reign, to appreciate the extraordinary rarity of our own solar system. Even our sun, a seemingly ordinary star to the naked eye, exhibits a set of characteristics that make it a remarkably rare beacon in the cosmos. While many stars can be categorized as similar to the sun, none exhibit the precise combination of mass, brightness, age, temperature, and composition that our sun does. Its stability is unparalleled. Its brightness fluctuates by only 0.1% over time. This is an essential trait for life. Even small, seemingly insignificant variations in a star's energy output could trigger catastrophic climate changes on a planet. Our sun's unyielding consistency provides the steadiness necessary for life to evolve and thrive. But the sun's stability is just one facet of the perfect cosmic conditions required to sustain life. The very structure of our solar system itself seems uniquely tailored to our survival. The gas giants, Jupiter and Saturn, occupy just the right positions in our solar system, acting as cosmic bodyguards for Earth. Their immense gravity acts as a shield, protecting the inner rocky planets from constant bombardments of asteroids and comets. Without these giants, Earth would have been hit by devastating space debris far more frequently, possibly preventing the development of life. Then there's our moon, which plays a crucial role in stabilizing the tilt of Earth's axis. This stability is essential in maintaining consistent seasons over long periods of time. Without the moon, Earth's tilt would wobble erratically, leading to chaotic climate shifts. Such instability could have made it impossible for complex life forms to evolve. Even with these highly rare and finely tuned conditions in place, the greatest mystery of all remains: the origin of life itself. One popular hypothesis, known as panspermia, suggests that life may have arrived on Earth via comets or asteroids, carrying with it the building blocks of life. But even if life did indeed arrive in such a primitive form, the process of evolution that followed presents a staggering challenge. Life on Earth has endured some of the most extreme conditions imaginable. It has survived 2 global ice ages, one about 2 billion years ago, and another approximately 635 million years ago. These events, known as snowball Earth periods, should have wiped out life. Yet, ironically, they may have played a role in shaping the very existence of complex organisms. During the first snowball Earth event, photosynthetic microorganisms began to thrive, absorbing greenhouse gases from the atmosphere and producing oxygen, a vital ingredient for the emergence of complex life forms. The second deep freeze, while seemingly devastating, set the stage for what would become the Cambrian explosion, an extraordinary event that took place around 540 million years ago. During this period, life exploded into a wide variety of forms, including the emergence of the first primitive brains. This period marked the evolutionary foundation for almost all the animal groups that exist today. It was during this time that intelligence began to take shape. The tumultuous history of Earth, including the ice ages and mass extinctions, may in fact have been crucial in the development of intelligent life. If we were to find a planet where conditions remain stable and perfect for billions of years, chances are intelligent life would never evolve. The reason for this is simple. Complexity in life emerges when organisms are forced to adapt to challenges. In a stable, unchanging environment, there would be little need for intelligence or adaptability. Life might remain at the level of simple bacteria or algae, never progressing to more complex forms. In this way, struggle and adversity become integral to the evolutionary process. Life evolves not in the absence of difficulty, but because of it. It's this balance of stability and challenge that fosters the evolution of complexity. Evolution doesn't thrive when conditions are too easy or too extreme. Too little pressure and organisms stagnate. Too much pressure and life can't survive at all. This balance is essential, and it holds true across all life forms, from the simplest bacteria to the most advanced species. But even if all the right conditions align, an ideal star, a planet in the habitable zone, a stabilizing moon, protective gas giants, and the presence of water and atmosphere, none of it guarantees that life will appear. The foundation of life hinges on one simple but crucial factor: the existence of a self-replicating molecule. This molecule must be capable of copying itself and passing on genetic information. It is this molecule, perhaps more than any other factor, that serves as the first building block of life. But how did this molecule come to exist? The emergence of the first self-replicating molecule is a staggering puzzle. Even after years of research, scientists have not been able to create one from scratch in a lab, despite numerous attempts to simulate the conditions that would allow it to form. Eugene Koonin, a Russian-American evolutionary biologist, calculated the odds of such a molecule arising by pure chance. The number he arrived at is almost beyond comprehension, 1 in 10 to the power of 118. To put this in perspective, the total number of atoms in the entire observable universe is estimated to be only around 10 to the power of 80. The odds of life emerging spontaneously are so astronomically small that they defy human understanding. Faced with such an impossibly small chance, even brilliant scientists like Koonin have been forced to consider alternative explanations. One such possibility is the multiverse hypothesis, which posits that our universe is just one among countless others, each with its own physical laws and conditions. If an infinite number of universes exist, it's possible that one of them had the right conditions for life to arise. In such a scenario, the seemingly impossible odds against the emergence of life might not matter. The rarity of life's origin means that it may be a one-in-a-kind event, and we might be utterly alone in the universe. This possibility is unsettling for many, especially those who dream of making contact with extraterrestrial civilizations. But there's another even more profound challenge to consider: the rise of intelligence. Even if life exists elsewhere, it may not have evolved into anything resembling the complex, intelligent beings we are familiar with. The search for intelligent life in the universe, as we've come to understand it, is grounded in assumptions about what intelligence is and what form it might take. Our search for extraterrestrial intelligence has been relentless, from investigating thousands of UFO sightings to sending astronauts to the moon and exploring Mars with robotic probes. We've sent powerful radio telescopes into the cosmos, hoping to detect signals from distant civilizations. We've launched probes beyond the reach of the sun's gravitational influence, sending them into the vast unknown. Yet despite our best efforts, we have found nothing. For over a century, we have sent out radio and television broadcasts, hoping they might be intercepted by another civilization. We've sent intentional signals into space, bold and hopeful attempts to make contact. But for all our efforts, we find ourselves in the same position: silence. The collapse of the Arecibo radio telescope in Puerto Rico, once one of the most powerful instruments used in this search, marked a tragic moment in the history of SETI, the search for extraterrestrial intelligence. And yet, despite this silence, it would be premature to declare ourselves alone in the universe. As the famous astronomer Carl Sagan once said, "Absence of evidence is not evidence of absence." The silence may not mean no one is out there. It may simply mean that we have yet to find them. The idea of panspermia offers an intriguing possibility that life didn't originate on Earth, but traveled across space, spreading from one planet to another, carried by comets or asteroids. This theory suggests that life may not be as unique to Earth as we think. Yet, even if this is true, it doesn't solve the mystery of what life might look like elsewhere. Our search for life assumes that it will be like us, carbon-based, built on the same principles that govern life on Earth. But could life take an entirely different form? Scientists have long speculated about alternatives to carbon-based life, such as life forms based on silicon. At extreme pressures like those found on the gas giants in our solar system, nitrogen and hydrogen may combine to form complex compounds that could serve as the foundation for life. Life might exist in places we've never thought to look, deep inside the atmospheres of Jupiter and Saturn, for example, where conditions are radically different from Earth's. The challenge we face in searching for extraterrestrial life is not just that we don't know where to look, it's that we don't fully understand what we're looking for. What if alien civilizations exist, but they are nothing like us? What if the intelligence we seek is not based on the same principles of biology and cognition that we know? We impose human logic onto the universe, hoping to find something familiar, but what if we're looking for the wrong thing? This uncertainty is part of what makes the silence of space so unsettling. It's not just the absence of evidence, it's the possibility that we're searching in the wrong way altogether. If the rare Earth hypothesis is true, and intelligent life is extraordinarily rare, then the silence of space could be a reflection of our profound isolation. And yet, perhaps loneliness is not the greatest fear we should hold. As we continue our search, we face a future that is full of wonder, but also full of questions we may never be able to answer. Recently, a groundbreaking study published in Nature revealed something that could alter our understanding of the universe forever. Using the James Webb Space Telescope, astronomers identified 6 massive galaxies that appeared to have formed just 600 million years after the Big Bang. This discovery is astonishing because, according to current cosmological models, galaxies of such size should not have been able to form so early in the universe's history. Based on our understanding, these galaxies should have been far smaller, perhaps 10 to 50 times smaller due to the lack of matter needed to form such large structures. If these findings are confirmed, they could force a dramatic revision of our understanding of the universe's age, potentially pushing it back to an astonishing 26.7 billion years old, nearly twice as old as we previously thought. This discovery, if verified, would have profound implications for cosmology, challenging the very foundations of our understanding of space and time. As astronomer Erica Nelson remarked, even if just one of these galaxies is confirmed, it would stretch the limits of our current scientific knowledge. The mysteries of the cosmos continue to unfold, and with each discovery, we inch closer to answers that may change everything we thought we knew about the universe. However, a bold new concept has emerged, challenging our understanding of the universe in profound ways. Some researchers have proposed a radical idea that could reshape everything we thought we knew about cosmic structures: the concept of dark time. This theory suggests that cosmic structures, from galaxies to clusters of stars, may have developed at a far faster pace than we ever imagined. If this hypothesis turns out to be true, it would compel scientists to fundamentally reconsider the basic principles of how the universe evolved, prompting a major shift in cosmological thought. Despite the many mysteries still surrounding the size and structure of the universe, one assumption stands firm. If the universe has any boundaries, whether they are sharply defined or vague and indefinite, it should be theoretically possible to reach them. But what might such a journey entail? Let's embark on a thought experiment to explore this possibility. Imagine setting off in a spacecraft, traveling in a straight line, and heading off into the vast expanse of space. Would you ever reach an end to your journey? Would you find a boundary? And if so, what would it look like? Perhaps you would encounter an invisible barrier, or maybe you would pass through this boundary and discover something entirely new. But where would that take you? For centuries, humanity has pondered such questions. Ancient civilizations were obsessed with the idea of the universe having a center and an edge. These thoughts were captured in ancient myths and philosophical musings, which often depicted the cosmos as a vast, structured entity with definite boundary beyond which lay the unknown. One famous engraving from the 19th century illustrates the medieval perception of the universe's boundary beyond which mysterious forces govern the workings of existence. These ideas, although quaint by modern standards, reflected an enduring curiosity about the cosmos and our place within it. Fast forward to today, and we continue to grapple with the mystery of the universe's true nature. For example, if we look up at the night sky and focus on the red supergiant star Betelgeuse, what we see is not the star as it is right now. Instead, we are witnessing it as it was about 500 years ago, the time it takes for the light from Betelgeuse to travel to us. In reality, Betelgeuse may have already exploded into a supernova, but we wouldn't know until the light from that explosion finally reaches Earth. This delay in light travel isn't unique to Betelgeuse. It applies to all cosmic phenomena. Gravity, too, behaves in a similar way. We don't feel the sun's gravity in real time. Instead, the force we experience comes from where the sun was 8 minutes and 20 seconds ago, because that's how long it takes for both sunlight and gravity to travel to Earth. Imagine for a moment, if the sun were to suddenly disappear, we wouldn't immediately feel the consequences. Earth would continue to orbit as if the sun were still there for 8 minutes and 20 seconds. It would take that much time for us to begin drifting away, and only after that would the planets in our solar system start to move in different directions. The same principle applies to galaxies. The Andromeda Galaxy, the largest galaxy in our local group, is hurtling toward us at a mind-boggling speed of approximately 400,000 kilometers per hour. However, because we are seeing Andromeda as it was in the past, it is actually 900 light years closer to us than it appears. To put this in perspective, the closest star to our sun, Proxima Centauri, is about 4.24 light years away. Even with the fastest spacecraft we can currently build, it would take tens of thousands of years to reach that star. So the fact that Andromeda is nearly 1,000 light years closer than we think is a mind-blowing realization. When we peer deeper into space, we can only see as far as the light that has had time to travel to us since the beginning of the universe. The farthest point from which light has reached us is a staggering 46 billion light years away. But this presents an intriguing puzzle. If the universe is only about 13.8 billion years old, how can we see objects that are so far away? Shouldn't we only be able to see objects at most 13.8 billion light years distant? The answer lies in the phenomenon known as dark energy and the universe's rapid expansion. It's not that the light from these far-off objects traveled to us in a straight line over the course of billions of years. Instead, space itself has so much that we can now observe these distant objects, even though their light may have started its journey long before the universe reached its current size. This is why we can observe objects 46 billion light years away in every direction. This fact raises an even deeper question. While the observable universe has a limit, what about the actual universe? Does it extend beyond what we can see, and if so, where does it end? Is there a physical boundary, or does space continue on indefinitely? To explore this, let's dive into another thought experiment. What if we could build a spacecraft capable of traveling in a straight line, accelerating as fast as possible to try and reach the edge of the universe? Astronomer David Kipping from Columbia University has explored this idea in great detail. He proposed an interesting scenario in which we design a spaceship capable of accelerating indefinitely at a rate of 10 meters per second squared. Why this specific rate? Because at this rate, the passengers on board would experience a force equivalent to Earth's gravity, meaning they wouldn't feel the weightlessness typically associated with space travel. Instead, they would feel as though they were standing on solid ground, just as they do on Earth. For reference, the acceleration due to gravity on Earth is about 9.8 meters per second squared, but rounding it up to 10 simplifies the calculations. Let's consider what happens next. In the first second of travel, the spacecraft would be moving at 10 meters per second. After 2 seconds, it would be moving at 20 meters per second. By the end of the first hour, it would already be traveling at a staggering 35,283 kilometers per hour, zooming past the moon. After 1 week, the spacecraft would pass Saturn, and after 11 days, it would be beyond Neptune, the farthest planet in our solar system. However, this is just a thought experiment, and we are ignoring practical concerns like fuel requirements and the dangers of colliding with cosmic debris. After 15 months of this relentless acceleration, the spacecraft would have traveled 1 light year. But something strange begins to happen. According to Einstein's special theory of relativity, there is a limit to how fast any object with mass can travel. No object can ever reach the speed of light. In fact, protons in the Large Hadron Collider, the world's most powerful particle accelerator, can only approach light speed, reaching 99.9999999% of it without ever actually getting there. This means that our spaceship, no matter how fast it accelerates, can never reach the speed of light. However, as the spaceship gets closer to this limit, something bizarre occurs. According to special relativity, the faster an object moves, the slower time appears to move for it from an external observer's point of view. The closer the spacecraft gets to the speed of light, the more its time slows down relative to the rest of the universe. From the perspective of the crew aboard the spacecraft, however, everything would feel normal. Time inside the ship would move as usual, while, to the crew's astonishment, time outside the ship would appear to be speeding up. At 87% of the speed of light, the effects of time dilation would become noticeable. However, this time dilation would become more drastic as the spacecraft approaches the ultimate limit, the speed of light itself. The passage of time inside the ship would increasingly diverge from the passage of time outside it. And as this occurs, the universe outside would continue to evolve, as though the crew aboard the spaceship were watching time itself stretch and warp. Interestingly, in 1991, a mysterious particle from deep space reached Earth, puzzling scientists with its bizarre properties. This particle, which came to be known as the "Oh my God" particle, was so small, yet carried an amount of energy equivalent to a baseball traveling at 94 kilometers per hour, that it left scientists stunned. What was truly extraordinary, though, was its speed. The particle was traveling at a speed of 99.99999999999999999999999999999% of the speed of light, a rate so close to light speed that it defied all conventional understanding. To this day, scientists have no explanation for what could have accelerated this particle to such an extreme velocity. The origin and nature of this particle remain one of the greatest unsolved mysteries in modern physics. Thus, as we continue to explore the deepest reaches of space, we are confronted with fundamental questions that challenge our understanding of the universe, questions that push the boundaries of both science and imagination. The answers, if they exist, may lie beyond our current reach. Yet the pursuit of these answers continues, guiding humanity's quest for knowledge and our ever-deepening exploration of the cosmos. Recent observations from the Telescope Array project have revealed something truly extraordinary. These findings suggest that particle, one of the most enigmatic ever detected, may have originated from a region about 20 degrees wide in the direction of the Earth's major constellation, Auriga. But here's the catch. That's all we know. That's the sum of our current understanding. However, even this limited piece of information raises far more questions than answers. Just imagining the potential origins of such an incredible event sends a chill down your spine, for it hints at phenomena far beyond the reach of our current scientific grasp. Perhaps the most mind-boggling aspect of this discovery is the way time itself behaves when an object moves at nearly the speed of light. Time dilation, one of the most fascinating and baffling consequences of relativity, becomes so extreme for this particle that from its own perspective, time was almost entirely frozen. If you were to observe the particle from a stationary vantage point, the difference would be staggering. Its passage of time slowed down by a factor of 300 billion. Yes, you read that right, 300 billion. To put this into perspective, imagine a journey across the cosmos. Take the Andromeda galaxy, for example. At about 2.2 million light-years away from Earth, traveling there at the speed that our current spacecraft can achieve would take approximately 2.2 million years. A human lifetime wouldn't even make a dent in that journey. But for this particle, the experience was vastly different. The same journey to Andromeda would have felt like it lasted less than 5 minutes. It's almost impossible to fathom. It's as though time itself bends and warps, offering us a glimpse into the truly alien mechanics of the universe. Now, if you think that's already awe-inspiring, let's stretch this thought experiment even further. What if a spaceship were able to travel at these mind-bending speeds, fast enough to close in on the speed of light? What would happen if it simply kept going, never stopping, hurtling into the vastness of space? The concept of a point of no return enters the picture, a threshold that every astronaut would dread. In the universe, this invisible boundary lies about 8.3 billion light-years away. Beyond this distance, a spaceship would be in a perilous position. It would never be able to return, not because of a physical barrier, but because of the very fabric of space itself. Space, as it turns out, is expanding at a rate faster than the speed of light, and this expansion doesn't obey the conventional rules of physics. This may sound counterintuitive, but it's not a violation of relativity. The spaceship, by all means, would not be exceeding the speed of light. Instead, it is the space itself that stretches faster than light, carrying everything within it along for the ride. This process is very similar to how a slinky toy works. When you stretch it, each coil moves just a tiny distance from the next. But if you look at the opposite ends, they have moved a vast distance apart. The same is true for galaxies. It's not that they are speeding away from us at faster than light velocities, but the space between us and them is expanding rapidly, making them forever unreachable. Crossing the 8.3 billion light-year mark would be a cosmic death sentence for any spacecraft. No matter how advanced the technology, no matter how much energy is poured into the propulsion systems, the spaceship would only be moving farther away from home. No hope of returning, no possibility of reconnecting with Earth. It's a chilling concept, to be lost in the vast emptiness of space, cut off from everything known, forever drifting further away from the familiar. But before we succumb entirely to the immensity of these ideas, let's take a moment to step back and examine the universe we see today. The observable universe, the part of space we can currently see with our telescopes, spans a staggering 46 billion light-years in any given direction. However, this visible portion of the cosmos is constantly growing, expanding outward as space itself stretches. In fact, scientists estimate that in the future, this visible universe will reach a size of about 61 billion light-years. But here's the catch. Just because something is visible doesn't mean it's accessible. The force driving this expansion is a mysterious entity known as dark energy. Dark energy is accelerating the expansion of the universe, dividing it into different zones that are defined by how far galaxies are from us. Galaxies that are within about 15 billion light-years of Earth are still technically reachable. In theory, if we could travel at the speed of light, we might reach these galaxies. But the real strangeness starts to unfold as we look farther into space. Galaxies located between 15 and 46 billion light-years away are visible to us, but they are unreachable. No matter how fast we travel, they will always be receding from us at speeds faster than light. The expansion of space ensures that we will never reach them, no matter how much time passes or how advanced our technology becomes. Even more astonishing are the galaxies beyond 46 billion light-years. These galaxies, completely invisible to us today, will one day be within our view. The light from these distant galaxies will take billions of years to travel across the universe, eventually reaching us. So, future generations of humans, assuming they still exist, will be able to observe galaxies that we can't even detect right now. They'll witness the unfolding of the universe in ways that we could never have imagined. Yet, this comes with its own tragic truth. Beyond the 61 billion light-year mark, there are galaxies that we will never see, no matter how much time passes. These galaxies will always remain beyond our cosmic horizon, permanently out of reach. To highlight just how extreme the universe's expansion is, consider the distant galaxy GNZ11. This galaxy, one of the farthest discovered to date, is 13.4 billion years old. The light we see from GNZ11 today was emitted just 400 million years after the Big Bang. That's an unfathomable distance in both time and space. What we're witnessing is not just the light of a distant galaxy, but the light of the universe in its earliest moments, offering a glimpse into the very origins of existence itself. This is what makes the cosmos so breathtakingly mysterious. Every light we see is a snapshot of time, captured across the vastness of space, with the promise of discovery still hidden in its depths. The universe is expanding, and with this expansion, everything we know, every galaxy, every star faces an unimaginable fate. One of the most extraordinary examples of this process can be found in the galaxy GNZ11, which, as of now, lies approximately 32 billion light-years away from us. You might wonder how it's still visible to us today, given this vast distance. The truth is, it won't be visible forever. The light that GNZ11 emits at this very moment will never reach us again. The relentless expansion of the universe is pushing it away faster than its light can travel. And this phenomenon is not unique to GNZ11. It is happening to nearly all of the galaxies we currently observe. In fact, scientists estimate that more than 96.7% of the galaxies we can see today have already disappeared beyond our reach. Out of the estimated 4 trillion galaxies that we were theoretically supposed to observe over the course of human observation, 634 billion have already drifted beyond our ability to see them. That leaves only about 66 billion galaxies still within our observable universe. And it gets worse. Every second, approximately 60,000 stars fade from our view. That's tens of millions of stars vanishing every day. Stars that once existed within the observable universe. Imagine for a moment looking up at the night sky and knowing that the stars you see might have already burned out millions or even billions of years ago. Their light is still traveling through the vast stretches of space, slowly but surely reaching us long after they've ceased to exist. Now, amplify that concept, and you'll begin to grasp the scale of the problem. Entire galaxies, at this very moment, are disappearing from our reach, not because they are vanishing in a literal sense, but because space itself is expanding so rapidly that any new light they produce will never travel the distance to reach us. For all practical purposes, these galaxies no longer exist from our perspective. They continue to exist somewhere out there in the universe. But from our vantage point, they are locked away beyond our grasp. No matter how hard we try, we can never interact with them again. We cannot send signals to them, nor can we observe any new changes they might undergo. They are beyond our influence, erased from our reality by the very expansion of the universe itself. As the expansion continues and the forces driving it grow stronger, even galaxies that are relatively close to us will eventually drift into the void. Over time, each galaxy will be left alone, isolated, and detached from the rest. Stars will burn out, their fuel spent, leaving behind cold, lifeless remnants. The particles that form everything we know, planets, people, even atoms themselves, will ultimately decay. And, astonishingly, even black holes, those immense gravitational powerhouses that once seemed as though they could endure forever, will slowly evaporate through a process known as Hawking radiation. This might take an unfathomably long time, but eventually, even the mightiest of black holes will vanish. What will remain in the end? Just an empty, cold, dark void. A vast expanse stretching infinitely in all directions, with no stars, no galaxies, no matter. The only thing that will persist is dark energy, an enigmatic and powerful force responsible for accelerating the expansion of space. Dark energy is unlike anything we experience in our daily lives. Whereas gravity pulls things together, dark energy works in the opposite direction, pushing space itself apart. What's even more baffling is that dark energy doesn't weaken as the universe expands. In fact, as the universe grows emptier, dark energy remains constant, or perhaps even grows stronger. This creates a self-reinforcing feedback loop. The universe expands, which leads to more empty space, and in turn, dark energy accelerates the expansion even more. This cycle will continue endlessly, causing the universe to grow at an ever-increasing rate. In time, the distance between events in the universe will become so vast that nothing will be able to interact with anything else. Even light will be unable to bridge the enormous gaps. The universe will eventually be nothing but an infinite void, where nothing happens and nothing ever changes. This is the ultimate fate that awaits the cosmos. An empty, silent expanse that expands forever, never reaching an end. But let's step even further into the unimaginable. What if we could build a spaceship capable of traveling at nearly the speed of light? If a crew aboard such a ship set off on a journey and their clocks measured 200 years passing on board, the rest of the universe would have experienced something far more staggering. 10 to the power of 41 years, an unfathomable number of years, represented as a 1 followed by 41 zeros. By the time those 200 years passed, the universe would have undergone a complete transformation. Space would have stretched so far that the ship might be the only remaining object in the observable universe. No stars, no planets, no galaxies, just an endless void stretching in all directions. And no matter how fast the crew traveled, they would never reach the edge of the universe. This is because the expansion of space itself would outpace even their near-light speed journey. There is no boundary, no end to the universe. It isn't a matter of there being an edge where you can run into a wall or a boundary of some sort. The universe simply doesn't have one. This concept takes us into an intriguing, almost mind-boggling idea. What if the universe doesn't have an edge, but is also not infinite? For thousands of years, philosophers and scientists have wondered whether the universe is truly endless or if it has some kind of limit. A famous philosophical argument, while put forth by the Greek thinker Archytas more than 2,000 years ago, posed the question: if you could stand at the edge of the universe and throw a spear, what would happen? Would it hit a wall and bounce back? If so, what is on the other side of that wall? If the spear passes through, then the universe must extend even further. For centuries, this paradox stumped thinkers, but the answer may not be so simple. What if the universe has edges, but still goes on forever in a different sense? This idea connects to a surprising discovery made in the 19th century by the mathematician Carl Friedrich Gauss, who questioned whether space itself could be curved in a way we don't yet understand. Imagine living on the surface of a giant sphere, like the Earth. If you draw a triangle on this surface, its angles will add up to 180 degrees. But if you draw a giant triangle, one that covers a significant portion of the sphere, the angles will exceed 180 degrees because the surface is curved. Gauss suspected that space might have similar curvature, and his theories were later confirmed by Albert Einstein's theory of general relativity. In fact, modern measurements show that space is indeed curved, and that the angles of a triangle can add up to slightly more than 180 degrees, at least near Earth. But what does this imply for the shape of the universe? If space is curved on a large scale, it could suggest that the universe is finite, but still has no edge. One way to understand this is to think about the surface of a balloon. A two-dimensional being living on the surface of a balloon would never encounter an edge, but their world would still be finite. If they walked in one direction long enough, they would eventually return to their starting point. Now, imagine applying this concept to three-dimensional space. Could our universe be structured in such a way that if you traveled in a straight line long enough, you would return to where you started? The idea is difficult for us to imagine, but it's not outside the realm of possibility. Physicists have spent decades trying to understand the true shape of the universe, and over the years, they have identified 18 different possible shapes or topologies for the universe. These can be divided into two broad categories: orientable and non-orientable universes. To explain this, consider the example of a Mobius strip, a fascinating two-dimensional shape that has only one side. If you trace a path along its surface, you will eventually return to where you started, but your orientation will be flipped. What if the entire universe is structured like a Mobius strip, but in 3 dimensions? If that were the case, traveling through space might eventually bring you back to your starting point, but everything would be mirrored, completely flipped in orientation. This may sound like something out of science fiction, but mathematically, it's a real possibility. However, most cosmologists remain skeptical that we live in such a universe. One major reason for this doubt stems from the idea of a non-orientable universe. If the cosmos were structured in this way, there would likely be regions where normal matter and its opposite counterpart, antimatter, interact, resulting in significant energy emissions. Yet, no such emissions have been observed. While this observation doesn't completely rule out the theory, it does suggest that if these regions exist, they are far beyond the observable reach of our current instruments. This brings us to how scientists test such ambitious ideas. They often rely on measuring the curvature of space across vast distances, particularly in proximity to massive objects like stars and black holes. It is well established that space is curved, but when viewed on a much larger scale, the data consistently points to a universe that is astonishingly flat, at least within the observable limits. If the universe is indeed flat, the implications are nothing short of profound. A flat universe on such grand scales hints that the cosmos might be infinite. In fact, a truly infinite universe would naturally appear flat at these vast distances, giving rise to some extraordinary conclusions. Theoretical physicist Max Tegmark delves into this concept in his book, Our Mathematical Universe, where he explores the staggering magnitude of possibilities. He calculated that the number of ways particles can arrange themselves within the observable universe is roughly 10 to the power of 10 to the power of 118, a number so vast that it is almost beyond comprehension. If the universe is truly infinite, however, then something even more remarkable must be true. Somewhere, far beyond the region we can observe, there must be another Earth, identical to ours in every way. Imagine for a moment that you draw a straight line from Earth in any direction. If you traveled a distance equal to 10 to the power of 10 to the power of 118 times the diameter of our observable universe, you would theoretically arrive at an exact replica of Earth. Not only would this Earth mirror ours, but there would also be an identical version of you, thinking the very same thoughts at this very moment. This idea might seem bizarre, even stranger than a mirrored universe, but the concept of an infinite universe suggests that every possible arrangement of particles must eventually exist, somewhere in its vast expanse, no matter how unlikely. Now let's take this thought experiment a step further. What if we consider not just infinite space, but also infinite time? The answer is both simple and profound. In a universe that is infinite in both space and time, everything that is physically possible must eventually occur. Even in regions where no particles exist, modern physics tells us that space is never truly empty. Quantum fields, the very foundation of the universe, are in a constant state of fluctuation. These fluctuations, known as quantum fluctuations, are an unavoidable consequence of Heisenberg's uncertainty principle. Over the course of time, these fluctuations could lead to highly unusual events such as the spontaneous formation of complex structures or even the appearance of an entirely new universe, seemingly out of nothing. While this might sound like pure science fiction, it is in fact a natural prediction of quantum physics. Imagine a universe so vast and endless that even the most improbable events are not just possible, but guaranteed to happen. You might be thinking, wait, are you really suggesting that if we wait long enough, something as absurd as a grand piano materializing out of thin air in the middle of an empty space could actually happen? As wild as it may sound, this idea has been taken seriously by some of the most brilliant minds in modern physics, including Anthony Aguirre, Sean Carroll, and Matthew C. Johnson. They ran the numbers and arrived at a startling conclusion. If you were to wait a period of time so long that it makes the current age of the universe seem like a mere blink of an eye, trillions of times longer, you would indeed witness something as improbable as a piano materializing before you. As unbelievable as it may seem, this all follows directly from the fundamental laws of physics as we currently understand them. The more unlikely an event is, the longer it takes for it to occur. But in a universe with infinite space, infinite time, or both, even the most improbable events will not only happen, but they will occur an infinite number of times. This, then, is the unsettling reality of infinity. If time truly stretches on forever, our universe will inevitably repeat itself down to the finest detail. That means eventually you will watch this exact video again, not just once, but an infinite number of times. For some, this concept might be thrilling, but for others, it is nothing short of terrifying. It raises the unsettling question, is the universe truly infinite, or is there some kind of boundary to all of this? Some scientists argue that the universe could still be finite, but on an incomprehensibly vast scale, and that it might be curved in ways we have yet to measure. The tools available to us today suggest that the universe is flat with an accuracy of 99.75%. However, if it is not perfectly flat, it must be at least 400 times larger than the observable universe, spanning an unfathomable 37 trillion light years across. But here's the twist. Even if the universe is finite, that doesn't necessarily mean it's curved in the way we expect. Take, for instance, the surface of a cylinder. Geometrically, it's flat because parallel lines remain parallel, yet it can extend indefinitely. The universe might function in a similar manner. There is even the possibility that our universe could be shaped like a four-dimensional torus, an object that appears flat, yet if you travel far enough in a straight line, you would eventually loop back to where you started. In contrast, a four-dimensional sphere would behave differently. In this model, the angles in a triangle would add up to more than 180 degrees, and parallel lines would eventually meet. The true shape of our universe is something we may never be able to fully grasp as three-dimensional beings. To truly perceive it, one would need to exist in 4 dimensions. This leads us to a mind-bending idea. The edge of the universe is not some far-off boundary. It is, in fact, all around us. To understand this concept, imagine a world that exists in only 2 dimensions, a flat plane that might stretch infinitely or loop back on itself. Within this 2-dimensional world, 2-dimensional beings would exist, completely unaware of the 3rd dimension. To them, their world would appear complete. But from our 3-dimensional perspective, we could see every atom of their existence as if it were laid bare before us. The edge of their universe would be obvious to us, but to them, it would remain invisible. Now, apply this same logic to our 3-dimensional universe. The 4th dimension is not some distant realm. It surrounds us, permeating every single atom of our existence. We are completely immersed in it, yet we have almost no way of interacting with it. It is, quite literally, the true boundary of our universe, always present, but forever just beyond our reach. And beyond that, there remains an enigma, a mystery wrapped in the vast emptiness of existence itself. Imagine a place where nothing exists for an unfathomable distance, a place so utterly empty that it feels as though time itself has come to a complete stop. There is no light, no stars, no galaxies, just an endless abyss of absolute darkness stretching for what seems like forever. This is the universe's void. We live on a planet that orbits the sun, which in turn is part of the Milky Way galaxy. The Milky Way, however, does not exist in isolation. It is part of a collection of approximately 50 galaxies known as the Local Group. The Local Group itself is just a small portion of a much larger cluster called the Virgo supercluster. But this is just the beginning. The Virgo supercluster, along with many other superclusters, is a mere fragment of something even more immense, a gigantic structure known as the Laniakea supercluster. Unlike planets or moons revolving around a central body, these massive galactic clusters do not orbit a single point. Instead, they move under the gravitational pull of a mysterious anomaly at the center of our local cosmic neighborhood, the Great Attractor. Yet for our purposes today, we won't focus on this gravitational giant. Instead, we will turn our attention to something far more eerie, the vast, desolate nothingness that lies ahead of it. This empty region is called the dipole repeller, a place where the pull of gravity is so weak that matter seems to avoid it altogether. These barren areas in space are known as cosmic voids, and they are among the largest structures in the universe, comprising most of its volume. If we could observe the cosmos from a great distance, it would resemble a massive web with galaxies connected by luminous threads and separated by vast pitch-black voids. One of the most puzzling and terrifying of these voids is the Bootes void. Despite the seemingly even distribution of stars in the night sky, stars are actually clumped together in galaxies. These galaxies, in turn, form gravitational clusters, and the gaps between them might seem vast. However, when compared to the scale of cosmic voids, these gaps are minuscule. The Bootes void, one of the largest known voids in the universe, is located approximately 700 million light-years away from Earth in the direction of the Bootes constellation. It was first discovered in 1981 by astronomer Robert Kirshner and his research team. From the moment of its discovery, the Bootes void has baffled scientists with its vast emptiness. How could such a massive region of space be so devoid of matter? What could have caused this cosmic desert? To truly grasp the enormity of the Bootes void, consider this. Its diameter is estimated to be around 330 million light-years, which is approximately 27% of the total diameter of the observable universe. In comparison, the Milky Way galaxy, already mind-bogglingly vast, is only about 100,000 light-years across. In other words, you could fit over 3,000 Milky Ways side by side within the Bootes void. When scientists first began investigating the Bootes void, they expected to find thousands of galaxies scattered throughout the region. What they found, however, was something far stranger, an almost incomprehensible emptiness. What could have caused such a vast region to be devoid of matter? What secrets could this colossal void hold? However, the discovery of the Bootes void, a vast expanse of emptiness in the universe, shocked astronomers. Initially, when researchers first began examining this immense, nearly empty region, they were able to detect only 8 galaxies within its enormous stretch. Since then, the number of galaxies identified in the void has increased, but even today, only about 60 galaxies have been observed in this cosmic desert. To grasp how truly unusual this is, consider the Andromeda Galaxy, which is our closest galactic neighbor. Situated roughly 2.5 million light-years away, it is one of the many galaxies that make up our local group of galaxies. If galaxies were distributed evenly across the universe, you would expect the Bootes void to contain at least 2,000 galaxies. Yet it contains only a tiny fraction of that number, raising profound questions about the nature of the cosmos. Greg Aldering, an astronomer from the University of Minnesota, vividly illustrated the mystery of the Bootes void. He proposed that if the Milky Way were placed at the center of this void, we would have had no knowledge of the existence of other galaxies until the 1960s. The sheer emptiness of this space would have blocked our view of distant galaxies, rendering us unaware of the vast universe surrounding us. Such an absence of cosmic structures is staggering, and it has led scientists to describe the Bootes void as one of the most puzzling and strangest places in the universe. The density of galaxies in this region is so alarmingly low that it challenges the very understanding of how the universe should be structured. To further highlight just how bizarre this region is, consider the Milky Way's local neighborhood. Within just 3 million light-years, our galaxy is surrounded by more than 24 neighboring galaxies. In stark contrast, the galaxies within the Boots void are spaced an average of more than 10 million light-years apart, 4 times the distance between the Milky Way and Andromeda. If the universe were uniformly distributed, the Bootes void should contain at least 10,000 galaxies. The fact that it contains so few raises unsettling questions about the underlying forces that might have shaped this region. Scientists have attempted to calculate the exact volume of the Bootes void. Traditional units of measurement struggle to express the enormity of such a vast empty space, so a unit known as the parsec is used. 1 parsec equals approximately 326 light-years, and using this unit, astronomers estimate that the total volume of the Bootes void is about 236,000 cubic megaparsecs. To put it into perspective, if the void were filled with galaxies at the same density as the rest of the universe, it could contain thousands of times more matter than it currently holds. So, what exactly fills this enormous void? The paradoxical answer is almost nothing. The Bootes void is an eerie, cosmic desert, completely devoid of the matter that populates other parts of the universe. In places where galaxies thrive, stars, planets, gas clouds, and cosmic dust swirl together in a constant dance of creation and destruction. Yet, in the Bootes void, there is an unsettling silence. Even tiny particles like photons, the fundamental particles of light, are scarce in this dark stretch of space. Some researchers even refer to the Bootes void as the ultimate cosmic desert, because it is so devoid of matter and energy. The stillness within this void is so profound that some scientists speculate it may be a place where time itself seems to come to a halt. In most parts of the universe, galaxies are in constant motion. Interactions between stars, planets, and cosmic forces drive the passage of time, creating change and motion. But in the Bootes void, no such activity is evident. There are no significant forces at play here, only an unnerving stillness that extends across millions of light-years. To further emphasize this point, consider that dust and dirt, mundane nuisances here on Earth, are almost entirely absent in the Bootes void. But perhaps more remarkable is the fact that even fundamental particles, the building blocks of the universe, barely interact with one another. If a particle does interact, it could take thousands upon thousands of years for such an event to occur. This extreme emptiness has led to some fascinating and bizarre effects. For example, when streams of neutrinos, nearly massless particles, enter one side of the Bootes void, they pass through it without changing in any noticeable way. Similarly, photons, the particles of light, travel through this vast emptiness unaltered. In contrast, matter, much heavier than neutrinos or photons, does not share this fate. It is slowly drawn toward the outer edges of the void, where a few lonely galaxies still reside. Because of this peculiar characteristic, where light and energy remain largely unaffected, the Bootes void might one day serve as the ultimate time capsule. Imagine sending a beam of photons across this vast stretch of space, only for it to be rediscovered millions of years later, completely unchanged. It would be a relic of a distant, forgotten past. But this void could have more futuristic applications as well. With no intergalactic dust to slow down advanced spacecraft, it could serve as the perfect testing ground for cutting-edge space exploration. Perhaps one day, spacecraft could use the Bootes void to push the limits of speed, accelerating to 99.99% of the speed of light. Yet the biggest mystery surrounding the Bootes void is not just its potential uses, but how it even came into existence. Compared to the rest of the universe, the Bootes void is an anomaly of an entirely different kind. Some scientists propose that it was formed when several smaller voids collided and merged, much like tiny soap bubbles merging into a single larger bubble. In support of this idea, astronomer Greg Aldering noted that the galaxies within the void seem to be arranged in strange, tube-like structures. He suggested that these galaxies could be remnants of the boundaries where smaller voids once met before collapsing into this vast emptiness. If the universe continues for long enough, even these remaining galaxies may one day be pulled away by the relentless force of gravity, leaving behind an even purer, darker emptiness. But what if the explanation is even more outlandish? A more speculative theory posits that the Boots void may not have formed naturally at all. Instead, some believe that it could be the result of an ancient, hyper-advanced civilization. According to this theory, a Kardashev Type 3 civilization, one capable of harnessing the energy of entire galaxies, could have systematically expanded across this region of space. As it advanced, this civilization might have dimmed or completely hidden each star it encountered, perhaps by surrounding them with massive Dyson spheres, structures designed to capture all of a star's energy output. This theory could explain the near-perfect spherical shape of the Boots void and its eerie emptiness. Given that the Boots void is roughly 700 million light-years away from Earth, and that intelligent life could have emerged in the universe as early as 4 billion years ago, such a civilization would have had more than enough time to accomplish this mind-boggling feat of engineering. Of course, this idea is purely speculative, but considering how strange the Boots void is, it is a theory worth considering. One thing is certain: the discovery of the Boots void has forced astronomers to reconsider everything they thought they knew about the structure of the universe. It has prompted them to rethink the distribution of galaxies and matter across the cosmos. The existence of such a vast and empty region has opened up new lines of inquiry, challenging old assumptions and leading to fresh perspectives on the very fabric of reality itself. This journey of discovery is not just about the Boots void, it's about exploring the fundamental nature of existence itself. Have you ever wondered if there could be another version of yourself living a completely different life in a reality that exists alongside our own? Could it be possible that what we consider our reality is just one of many parallel worlds? Some scientists and philosophers suggest that our perception of life as a continuous journey through time and space may be an illusion. Instead of following a single unbroken path, our existence could be an endless, branching series of events, each splitting off into countless possibilities. If this idea holds true, then multiple versions of you exist simultaneously, each experiencing a different reality. In this sense, you might even be immortal, because somewhere in some other universe, another version of you is always alive. This fascinating idea leads us into the realm of the multiverse. There are intriguing discoveries that hint at the existence of such parallel worlds, including the cosmic microwave background radiation, CMB, a form of radiation that fills the cosmos. For decades, scientists have been captivated by the mysteries of CMB and its potential implications for the multiverse theory. As we explore this concept, we will also look into famous thought experiments like Schrödinger's cat and Albert Einstein's own theories. Along the way, we will uncover evidence that suggests the possibility of parallel universes and perhaps even other forms of life beyond our own. The story begins in 1948, when the brilliant physicist George Gamow, born in Russia but later a US citizen, made a groundbreaking prediction. He theorized that if the universe had indeed originated from the Big Bang, residual radiation from that event should still be detectable today. According to his calculations, this radiation should have a temperature of approximately 50 degrees Kelvin, or about 2,167 degrees Celsius below freezing. His theory would lay the groundwork for some of the most profound discoveries in modern cosmology, offering clues that might one day confirm the existence of the multiverse. In 1965, two American scientists, Arno Penzias and Robert Wilson, were working at Bell Laboratories when they unknowingly made one of the most groundbreaking discoveries in modern cosmology. At the time, their primary goal was to study neutral hydrogen, one of the most abundant elements in the universe. They were using a radio antenna, initially built in the early 1960s for an early communications satellite system. These satellites were no longer in use and had already been safely deorbited, re-entering Earth's atmosphere and burning up. Penzias and Wilson, however, were not expecting to uncover something entirely unexpected. Instead of observing the expected signals, they were consistently interrupted by a strange, unexplained microwave interference. Despite their best efforts, the interference would not go away. At first, they thought the disturbance might be the result of some sort of military testing or perhaps radio interference from nearby New York City. When this hypothesis proved to be incorrect, they even entertained the idea that pigeon droppings on the antenna might be causing the problem. After all, the antenna's design had proved to be a perfect nesting site for birds. However, even after thoroughly cleaning the equipment, the mysterious noise persisted. It wasn't until later that they realized they had accidentally discovered something extraordinary: the cosmic microwave background, CMB radiation, a relic from the Big Bang, the very radiation that scientists had been searching for decades. Their discovery turned out to be a monumental confirmation of one of the central predictions of the Big Bang theory, proof that the universe began in an incredibly hot and dense state and has since been cooling and expanding. For this serendipitous thinking work, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. What made this radiation so significant was not just the fact that it was found, but the fact that it was everywhere. It wasn't just coming from one direction of the universe. It permeated the entire cosmos. No matter where astronomers pointed their instruments, the temperature of the radiation remained constant. It was as though the universe was surrounded by an invisible ocean, one that you couldn't see, but could feel. This ocean of radiation existed at a temperature of 2.7 degrees Kelvin, only a tiny fraction above absolute zero, but it was ubiquitous. Yet, as scientists delved deeper, they realized that while the CMB appeared remarkably uniform, there were small but significant temperature fluctuations. These tiny variations, averaging about 18 microkelvin, were incredibly subtle but still visible. If you were to map the temperature of the CMB across the sky, it would look like a patchwork quilt or gentle ripples spreading across a pond. Fast forward to 2004, when NASA's WMAP, Wilkinson Microwave Anisotropy Probe satellite, began its more detailed study of the CMB. The WMAP mission aimed to map out these tiny temperature fluctuations at ones that had existed in the universe when it was just 380,000 years old, just a fraction of a second in cosmic time. As the data was analyzed, scientists found something astonishing. In one region of the sky, there appeared a cold spot that was significantly colder and much larger than anything they had anticipated. This cold spot, which would go on to spark numerous debates and discussions among physicists, was something that just didn't fit the usual patterns. The temperature fluctuations in the CMB are typically measured in the range of 18 microkelvin, but this cold spot was measured to be about 70 microkelvin, much colder than the surrounding radiation. In fact, at its center, the temperature could drop as low as 50 microkelvin. To give some perspective, imagine an ocean where the average wave height is just a few centimeters, and then, out of nowhere, a massive towering wave emerges, stretching several meters high. That's the cosmic equivalent of this cold spot, a strange anomaly in an otherwise even temperature field. To make things even more extraordinary, the cold spot wasn't small. It was vast, spanning nearly 2 billion light-years across the cosmos. For comparison, the Milky Way galaxy, the very galaxy we reside in, is only about 100,000 light-years wide. This cold spot could easily fit 20,000 galaxies of the Milky Way inside it, all with room to spare. If that scale doesn't quite hit home, consider this. The land area of the United States is roughly equivalent to 8,000 copies of New York City. Now imagine a cosmic void that dwarfs this comparison by a factor that's almost impossible to grasp. Astronomers believe that this cold spot is linked to an enormous void in space, a vast region that is nearly devoid of galaxies, stars, and other cosmic structures. This area, located in the Eridanus constellation, has been named the Eridanus supervoid. If you could somehow venture into the heart of this supervoid, you would find yourself in a truly alien environment. Absolute darkness, with no stars to guide your way, no galaxies to orient yourself with, just an endless, freezing expanse of emptiness. It would be one of the most desolate and mysterious places imaginable, perhaps the darkest corner of the entire universe. This leaves us with one fundamental question. How did this void come to be, and could it provide us with clues about the very nature of our reality? Some researchers have proposed an intriguing hypothesis. Perhaps this supervoid is not simply an empty gap in the cosmic fabric, but the result of something far stranger, the aftermath of a collision between our universe and another universe in the multiverse. According to this theory, the cold spot could be the remnant of a cosmic interaction between parallel realities, one universe brushing against another. If this idea holds any weight, the cold spot might be the first tangible evidence that parallel universes exist, a monumental discovery that could fundamentally change our understanding of the cosmos. Although this theory remains speculative, it's a tantalizing possibility that some of the world's leading physicists are taking seriously. The very idea that our universe may not be the only one, but part of a much larger multiverse, is an idea that has captivated imaginations for decades. And if the Eridanus supervoid is indeed a remnant of a cosmic collision between parallel universes, it could open the door to an entirely new frontier of scientific exploration. For many years, scientists have studied the vast empty spaces scattered throughout the universe, regions known as cosmic voids. These voids, which can span hundreds of millions of light years across, are some of the least dense areas in the universe. In fact, compared to the more densely packed regions of the cosmos, voids contain roughly 10 times less matter. The first discovery of these voids came in 1978 when astronomers Stephen Gregory and L. Schrey Thompson, working at the Kitt Peak National Observatory in Arizona, identified these vast gaps in the cosmic web. These voids vary widely in size, ranging anywhere from 30 million to 300 million light-years across, and they continue to be a subject of intense study. What is their true nature, and what secrets could they hold about the formation and evolution of the universe? Only time and further research will tell. However, one particular cosmic anomaly, known as the Eridanus supervoid, defies every expectation. This region of space is so vast that it stretches across nearly 2 billion light-years, a size that completely eclipses any other void previously discovered in the universe. Its immense emptiness raises some troubling and perplexing questions about the very fabric of the cosmos. The most widely accepted theory of the universe's birth, the Big Bang model, posits that the universe expanded uniformly from a singularity. Yet, if the universe truly expanded in such a way, how could such an enormous empty space have formed? The discovery of the Eridanus supervoid has created a serious challenge for this theory, since the void is not only massive but also unusually cold, much colder than the surrounding space. Standard cosmological models can explain the existence of smaller voids, but something on this scale, so vast and so frigid, shouldn't even be possible. Since its discovery, scientists have been scratching their heads, offering a wide range of speculative hypotheses to explain this anomaly. Some of these theories are grounded in established science, while others veer into the truly mind-bending realms of physics. Let's explore a few of these theories in detail. One of the first ideas proposed was that the Eridanus supervoid could actually be the imprint of a supermassive black hole. Black holes are known for their intense gravitational pull, capable of swallowing everything in their path, leaving behind enormous voids. But could the supervoid be the result of such an astronomical entity? While this theory might seem plausible at first glance, it soon runs into a few insurmountable problems. First, the void is situated about 3 billion light-years away, meaning any black hole in that region would take an incomprehensibly long time to affect our part of the universe. Furthermore, calculations reveal that the mass of a black hole capable of creating such a massive void would need to be staggeringly large, far beyond anything current science has been able to understand. To put this into perspective, even a black hole with the mass of 100 million suns would still be far smaller than our own sun in terms of its physical size. This means that despite its immense gravitational pull, it would be unable to generate the kind of vast empty space that the Eridanus supervoid represents. So, while the black hole theory sounds intriguing, it ultimately fails to account for the true nature of the void. Another possibility arises from the strange, invisible substance that comprises the bulk of the universe's mass, dark matter. This elusive material does not interact with light or electromagnetic forces, making it invisible to our instruments. However, its presence can be inferred through its gravitational effects on visible matter. According to current cosmological models, every region of space, including voids, should contain at least some amount of dark matter. Yet, when researchers studied the Eridanus supervoid, they found something unsettling. There was no sign of dark matter at all. If this void lacked the expected amount of dark matter, its radiation signature would differ, and its gravitational pull would be stronger. This curious absence opens up a disconcerting possibility. What if dark matter, the very foundation of much of modern cosmology, doesn't exist after all? If the Eridanus supervoid truly lacks dark matter, it could challenge the very framework of the Big Bang theory. Without dark matter, many of the equations used to describe the universe's structure would break down. However, before we completely discard decades of research, it's crucial to note that there is still significant evidence supporting the existence of dark matter. The mystery persists. Why is the Eridanus supervoid seemingly devoid of it? If neither black holes nor missing dark matter provide the answers, some scientists have begun to look beyond our universe for an explanation. According to a bold and extraordinary hypothesis, the Eridanus supervoid could be the first tangible evidence of a multiverse, an idea that suggests our universe is just one of many existing simultaneously in a vast cosmic sea. But how could we detect the presence of another universe? The answer may lie in the cosmic microwave background CMB radiation, a faint afterglow of the Big Bang. This radiation acts like a fingerprint, capturing the earliest moments of the universe's existence. Strangely, when astronomers studied the CMB map, they found a cold spot exactly where the Eridanus supervoid is located. This suggests that something truly unusual occurred in that region billions of years ago, something that current physics cannot fully explain. Could this cold spot be the trace left by a collision between universes? Some physicists propose that our universe may have collided with another in the distant past, leaving behind a distinct imprint in the CMB. In this case, the Eridanus supervoid might represent the site of a cosmic collision where two bubble universes came into contact with each other. The work of physicists such as Anthony Aguirre, Matt Johnson, and Matt Klaban supports this idea. Their research suggests that if our universe had ever collided with another, it would have left behind a circular mark in the CMB. Remarkably, this is precisely what we observe in the Eridanus supervoid. If this hypothesis is correct, it would be one of the most groundbreaking discoveries in the history of science. It would confirm that our universe is not alone in the cosmos, and that other universes may exist, each with its own stars, planets, and potentially even intelligent civilizations. To truly grasp the significance of the multiverse theory, we must briefly explore the strange and counterintuitive world of quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales. One of the most famous experiments in quantum mechanics is the double-slit experiment. In this experiment, scientists shine light or shoot tiny particles through two slits in a barrier and observe the pattern they create on a screen behind the barrier. When light or waves pass through the slits, they create an interference pattern, a series of bright and dark bands. This is because the waves overlap and combine in certain areas while canceling out in others. However, when scientists perform the same experiment with particles, like electrons, something bizarre happens. Instead of forming two distinct lines on the screen, the electrons behave like waves, creating the same interference pattern. This means that the individual particles, which should behave like tiny solid objects, are instead behaving like waves. But how could this happen? The mystery deepens when scientists fire electrons one at a time. Each electron should pass through one slit or the other, but instead, the electrons create the interference pattern as if they were passing through both slits simultaneously. To solve this puzzle, scientists decided to observe which slit each electron passed through. But as soon as they began to measure the electrons, the interference pattern vanished. The electrons stopped behaving like waves and acted like particles again, forming two distinct lines on the screen. This suggests that the mere act of observation changes the behavior of the particles. How could this be? Does the universe behave differently depending on whether someone is looking at it? This strange discovery has led to some of the most perplexing and mind-blowing theories in physics. One of the most intriguing possibilities is the many worlds interpretation of quantum mechanics, which suggests that every time a quantum event occurs, the universe splits into multiple realities. If this is true, then the multiverse theory becomes more than just a theoretical concept. It could be a direct consequence of quantum mechanics. In this context, the Eridanus supervoid might not just be a mysterious region in our universe, but the first physical evidence of another universe, a separate reality that collided with ours in the distant past. This theory, while still highly speculative, has captured the imagination of many physicists. If proven true, it would fundamentally change our understanding of reality itself, opening up possibilities that stretch far beyond our current comprehension. Whether the Eridanus supervoid is the result of a cosmic collision, a missing piece of dark matter, or something entirely unknown, it remains one of the greatest mysteries of modern science, one that challenges the very foundations of the universe as we know it. The mystery of our universe deepens in some of the most extraordinary ways, and perhaps no explanation has captured the public's imagination more than the strange and paradoxical nature of quantum mechanics. One of the most famous ideas to emerge from this field comes from two of the greatest minds in physics, Werner Heisenberg and Niels Bohr. In the early 20th century, they proposed what would become known as the Copenhagen interpretation of quantum mechanics. This groundbreaking theory suggests that before we observe a particle, it does not exist in a single, well-defined state. Instead, it exists in all possible states at once, a kind of blur of potential outcomes. Only when we observe the particle does it choose one of those states. In other words, reality itself is altered by the act of observation. For example, an electron is not truly in one place or another until we look at it. Before we measure it, the particle could theoretically be everywhere at once. This idea rattled many physicists, including the brilliant Albert Einstein, who famously rejected it with the famous phrase, "God does not play dice with the universe." Einstein's words echo a deep skepticism about randomness and probability ruling the cosmos. He believed that there must be a more deterministic, ordered nature to reality. Einstein's doubts were shared by other physicists, including Erwin Schrödinger, who created a thought experiment in 1935 to highlight the absurdity he saw in the Copenhagen interpretation. Schrödinger imagined a cat inside a box with a radioactive atom. The atom has a 50% chance of decaying within an hour, triggering a mechanism that releases poison gas, killing the cat. If the atom doesn't decay, the cat remains alive. According to quantum mechanics, until someone opens the box to check, the atom is in a superposition. It is both decayed and not decayed at the same time. Therefore, the cat must also be in a superposition, both alive and dead simultaneously. It's only when the box is opened and an observation is made that the cat's fate is sealed. Schrödinger presented this as a criticism, not as a literal description of reality, but as a way to show how bizarre and unintuitive the quantum world was. Yet this brings up a crucial question. If that's not how reality works, then what is really going on? One intriguing possibility, known as the many worlds interpretation, suggests that all possibilities occur, but in separate parallel universes. Every time a decision is made, the universe splits into multiple realities. For instance, if you flip a coin, one universe exists where it lands on heads and another where it lands on tails. In the context of the double-slit experiment, this theory posits that an electron passes through one slit in one universe and through another slit in a different universe. We see only one outcome because we are inside just one of these countless branching realities. Though this idea might seem like pure science fiction, it has garnered serious attention from some of the world's top physicists, including Hugh Everett, who proposed it in 1957. But perhaps the most mind-boggling theory of all is the suggestion that reality itself is not real. What if our entire universe is merely a simulation, a kind of sophisticated computer program running on an unimaginably powerful system? Just like a video game where objects only render when the player looks at them, what if our world behaves in the same way? What if electrons and other fundamental particles only exist when we observe them? The idea might sound far-fetched, but some scientists argue that it could explain strange phenomena in physics. Consider the staggering advancement of computers over the past century. Since the 1940s, their processing power has increased by several orders of magnitude, hundreds of trillions of times more powerful than they were just a few decades ago. And the rate of growth isn't expected to slow down. In the coming decades, experts predict that computing power could increase by millions of times. This exponential growth in computational capacity could one day make it possible to create virtual worlds so complex that the inhabitants of these worlds would possess thoughts, emotions, and even consciousness, yet they would remain unaware that they were part of a simulation. This leads to a chilling question. What if we are those simulated characters? Elon Musk, one of the most prominent advocates of this idea, has argued that there is a 1 in a billion chance that we are living in base reality, the real world as we typically think of it. Musk is not alone in his beliefs. More and more scientists and philosophers are coming to the conclusion that we may be living in a simulated reality. To understand why this is even a possibility, it helps to think about how computer simulations and virtual worlds function. In a video game, for example, the game world only renders what's in front of the player's character. Everything behind them doesn't exist until they turn around. This concept is familiar to anyone who has used a virtual reality headset. When you look straight ahead, the world around you seems normal, but the instant you turn your head, the system generates a new scene in real time, and the old one disappears. What if this applies to our universe as well? What if reality is rendered only when observed? Could it be that our universe behaves like a virtual world, only fully existing when we look at it? One of the most curious phenomena in quantum mechanics is called the observer effect. This is best illustrated by the famous double-slit experiment, conducted by Thomas Young in the early 19th century. When scientists shine light through two slits in a screen, the light behaves as a wave, spreading out in all directions. But when they observe which slit the light passes through, something strange happens. The light stops behaving like a wave and instead acts like a particle. In other words, light behaves differently depending on whether or not it's being observed. This seems impossible, but experiments have confirmed that this is how the quantum world works. Imagine this scenario. You have a cup of coffee in front of you. When you look at it, it's just a cup of coffee. But if you look away for a second, the cup transforms into the sound of ocean waves. This sounds absurd, but this is exactly the kind of behavior observed at the quantum level, where particles like electrons and atoms change based on observation. But what if our universe itself is like that? What if it's a simulation that only renders things when they are observed? Could it be that we're living in a giant, complex video game? The idea may sound bizarre, but it's one of the many possibilities being seriously considered by modern physicists. In addition to these peculiarities of observation, one of the most fundamental and unchangeable rules of the universe is the speed of light. This constant is a fundamental law of physics. Nothing can exceed the speed of light, which is approximately 300,000 kilometers per second. It may seem like an arbitrary restriction, but what if it's not? What if the speed of light is not a natural law, but rather a feature of the system that governs our reality? Much like a computer processor has a maximum speed that it cannot exceed, could the speed of light be a limit imposed by a larger system, perhaps a simulation? This idea gains further weight when we examine another strange phenomenon, time dilation. According to Einstein's theory of relativity, as an object approaches the speed of light, time slows down for it. For example, if you were traveling in a spaceship that moved at the speed of light, time would stop for you. From your perspective, you would reach a distant galaxy in an instant, but for people on Earth, billions of years would pass. The faster you travel, the more time slows down. But here's the kicker. Light particles, or photons, experience no passage of time at all. Time dilation suggests that time itself is connected to the speed at which objects move. But could this phenomenon be a feature of a simulated reality, rather than a natural law of the universe? After all, in a digital simulation, time could be controlled by the system's clock speed, much like how a processor determines the rate at which a computer operates. There's even more evidence to suggest that our universe may have a digital nature. In modern physics, there is something known as the Planck length, the smallest possible measurement of space. It is roughly 1.6 by 10 to the 35 meters, and nothing can be smaller than this. It's as if space itself is made up of tiny, indivisible units like pixels on a screen. In addition, there is Planck time, the smallest unit of time, approximately 5.4 by 10 to the 44 seconds. This means that the universe doesn't flow smoothly. Instead, it operates in discrete, rapid flashes, like the frames of a video game. If the universe is like a video game, it could be refreshed countless times per second, much like a high-speed computer screen refreshes at 60 frames per second. The only difference is that this refresh rate would be far beyond our perception. Finally, there's quantum entanglement, one of the strangest phenomena in physics. When two particles become entangled, changing one particle instantly changes the other, no matter how far apart they are. This happens faster than the speed of light, defying our understanding of causality. Einstein famously referred to this as spooky action at a distance. But what if this is how a simulation works, instantaneous changes across vast distances, governed by the underlying code of reality? The more we uncover about the universe, the stranger it becomes. And maybe, just maybe, we are part of a vast simulated reality. The possibilities are endless, and perhaps in time we will come to understand the true nature of the world we live in. Until then, we can only wonder, is our reality truly as it seems, or is it something far more intricate and mysterious than we ever imagined? Experiments have repeatedly confirmed that quantum entanglement is real. But what if, instead of merely being a strange quantum phenomenon, it offered a clue to something even more extraordinary? Imagine for a moment that our universe is not a vast, continuous natural expanse, but rather a massive, intricately designed computer simulation. In such a scenario, quantum entanglement might be analogous to how data is stored and retrieved in a digital system, like a video game where two characters, no matter how far apart, remain connected by code. Could this instantaneous connection between entangled particles be pointing us toward the possibility of a universe where everything operates within a hidden computational framework, a universe governed by rules of information? To consider this further, physicists have often described the speed of light not just as a speed limit, but as the fastest rate at which information can be transmitted. In other words, the universe in this view might be behaving less like a physical entity and more like a giant information processing system, much like a computer simulation. Within the confines of digital systems, there are always limits on how quickly data can be processed. And so, if our reality were indeed digital in nature, the speed of light could simply represent the maximum rate at which data can be transferred within the system. This idea might sound like pure science fiction, but it has intrigued many scientists who have begun to take it seriously. Some have even proposed experiments to test whether the fabric of space-time itself is not continuous, but made up of tiny indivisible units, much like pixels on a computer screen. If these experiments find evidence that space and time are indeed granular, this would lend strong support to the notion that our reality is not continuous, but instead digital. If this hypothesis holds true, then what we've always thought of as a boundless natural universe could in fact be a finely tuned digital construct running on an immensely powerful computational system. The evidence for this idea might be surprising, and it stretches across multiple fields of physics: the speed of light, the pixel-like nature of space-time, and the peculiar relationship between motion and quantum behavior, especially the strange properties of quantum entanglement, might all hint at a reality that behaves more like a high-tech simulation than a purely physical world. Take, for instance, the behavior of entangled photons. Initially, scientists believed that these photons might contain information about their spin before being measured. This belief was consistent with classical ideas about physics, where the properties of an object are assumed to be determined before they are observed. However, in the years following Einstein's era, experiments inspired by Thomas Young's famous double-slit experiment, which had already been scrutinized extensively, revealed something truly baffling. Contrary to expectations, these tests consistently showed that entangled photons had no predefined spin. Instead, their spin only emerged the moment they were measured, almost as if their state was decided at the moment of observation. This discovery seemed to support Einstein's skepticism about quantum mechanics, suggesting that something was fundamentally flawed in the theory. However, a groundbreaking experiment in 1964, conducted by physicist John Bell, would radically shift this understanding. Bell's experiment tested whether particles like photons carried hidden information about their spin before being measured. The results were nothing short of astonishing. Bell's work conclusively demonstrated that particles did not have a defined spin prior to measurement. Rather, they existed in a state of uncertainty until they were observed. This shattered classical ideas of physics, exposing the flaws in the common comparison between quantum entanglement and pairs of gloves, where one glove is predetermined to be left-handed and the other right-handed. The analogy was simply inaccurate. What made this discovery even more extraordinary was that entangled particles seemed to communicate their state to each other instantaneously, even at vast distances. This mysterious connection between distant particles baffled physicists, as it appeared to defy the constraints of classical physics. According to Einstein's theory of relativity, nothing can travel faster than the speed of light. But in quantum entanglement, particles seem to communicate their states instantaneously, no matter how far apart they were. If one photon, for example, was measured and found to have an upspin, the other photon, no matter how far away, would immediately take the opposite downspin. To further explore this peculiar phenomenon, a team of Swiss scientists from the University of Geneva conducted an experiment in 2008. They separated two entangled photons by 11 miles, or 18 kilometers, and measured one of them, closely monitoring the speed at which the other photon responded. Their instruments were so precise that they could detect even the tiniest delay, down to speeds 100,000 times faster than light. However, they found no delay whatsoever. This suggested that quantum entanglement might not just be faster than light, it might be instantaneous. Einstein once famously argued that no information could travel faster than the speed of light. But what if he was mistaken? Not about the physical universe itself, but about the very nature of the universe. What if our reality wasn't purely physical at all? What if it were more like a vast interconnected digital simulation? If we imagine photons as tiny pixels on a screen, the puzzle begins to fit together more neatly. In a simulation, two entangled photons might behave as pixels connected by a shared program. If one photon is given an upspin, the other automatically receives the downspin, no matter the distance between them. In this case, distance becomes irrelevant because the program controlling the simulation doesn't need to physically move data. It simply updates the state of the program in real time. This hypothesis, if true, could also offer a surprising explanation for one of the greatest mysteries in science, the Fermi paradox. This paradox asks, if intelligent extraterrestrial life is so likely to exist in the vastness of the universe, why haven't we found any evidence of it? Perhaps the answer is far simpler than we expect. Maybe extraterrestrial civilizations aren't programmed into our simulation. If that were the case, the moment we encounter alien life might not be a random event, but rather a decision made by the creators of the simulation itself. After all, in a digital simulation, new elements can be introduced at any time, reshaping the world as we know it. In fact, there's another strange phenomenon that has left people questioning not only the nature of reality, but also the reliability of their own memories. This phenomenon, known as the Mandela effect, first came to light in 2009 when a researcher named Fiona Broom uncovered a puzzling detail. For as long as she could remember, she had been absolutely certain that Nelson Mandela, the famous human rights activist, had died in prison during the 1980s. She vividly recalled news reports, newspaper headlines, and public mourning over his death. But when she did some research, she was shocked to discover that Mandela had actually been released from prison in 1990 and went on to serve as the president of South Africa until his death in 2013. At first, it seemed like a simple case of misremembering. But what made this discovery extraordinary was that Fiona was not alone in her false memory. When she asked others, she found that many people shared the exact same belief that Mandela had died decades earlier. Some even claimed to have watched his funeral on television, hearing his daughter deliver an emotional eulogy. This collective misremembering led Fiona to investigate further, and she was stunned to find that thousands of people from all around the world had the same false memory. Many of them were equally shocked when they learned the true timeline of Mandela's life and death. The phenomenon Fiona Broome uncovered came to be known as the Mandela effect, and it didn't stop there. With the rise of the internet and social media, people from different countries and cultures began to share their own strange memories that didn't align with reality. Some of the most famous examples included the Volkswagen logo mystery, in which people claimed to remember the logo being different, with a gap between the V and the W that wasn't there. What if these inexplicable memories weren't just coincidences? What if they were a glitch, an anomaly in a larger digital system, one that reshapes reality itself? This phenomenon, along with the strange behavior of quantum entanglement and the possibility of a digital universe, might suggest that our reality is not as solid and unchangeable as we once thought. Instead, it could be part of a larger, much more complex system, one that is constantly evolving, updating, and reshaping itself in ways we are only beginning to understand. There's a strange phenomenon that's fascinated millions of people for years: the Mandela effect. Thousands, even millions of individuals recall certain events, logos, or details in ways that are vastly different from how they actually occurred. Take, for example, the widely recognized logo of Gap, the global clothing retailer. Countless people insist that the iconic logo once had the word "the" written in front of it, the Gap. Yet as far as history shows, the logo has always been the simple word Gap. Similarly, the well-known mascot from the Monopoly board game is often pictured by fans with a monocle. Yet the Monopoly man, often confused with the image of a wealthy businessman or aristocrat, has never sported one. This vivid image of the monocle seems to be an artifact of collective memory, despite it never being there. These shared yet incorrect memories stretch even further. Take, for instance, the infamous peanut butter brand many recall as Jiffy. People are adamant that such a product once existed. However, no such brand ever existed under that name. The peanut butter in question has always been Jif, and it seems that many have simply merged the name with that of another peanut butter brand, Skippy, creating a memory of a brand that was never real. Perhaps one of the most curious examples comes from the Pokemon franchise. Many people remember Pikachu, the beloved electric mouse, as having a black tip at the end of his tail. However, this image is completely inaccurate. Pikachu's tail has always been entirely yellow. It's a detail that fans have strongly insisted on, but he does not match the popular belief. Similarly, C-3PO, the iconic droid from Star Wars, is often thought to be entirely golden. Yet in every film, C-3PO has had one silver-colored leg, a detail that even the most devoted Star Wars fans often overlook. These are only a few of the countless examples that make up the Mandela effect, a phenomenon that continues to baffle people around the world. What makes it so perplexing, though, is not simply that individuals misremember events, but that large groups of people seem to share identical, yet incorrect, memories of things that never happened. This collective false recollection, stretching across borders and cultures, raises intriguing questions about the very nature of memory, perception, and reality itself. Over the years, numerous researchers, psychologists, and even conspiracy theorists have attempted to explain the Mandela effect. One of the more mind-bending hypotheses suggests that these collective misremembrances may be the result of glitches in the fabric of reality itself, something akin to errors in a computer program or a simulated environment. This theory draws inspiration from the concept known as the simulation hypothesis, which proposes that our universe is, in fact, a highly advanced computer simulation created by a higher intelligence. Although this may sound like the stuff of science fiction, the simulation hypothesis has garnered serious attention from philosophers, physicists, and computer scientists alike. To understand why some thinkers seriously entertain the possibility of a simulated reality, one must first look at the rapid and unprecedented advancements in computing technology over the last century. In the 1940s, the world's first true programmable computer, ENIAC, was capable of performing a mere 5,000 calculations per second, a groundbreaking achievement at the time. Fast forward to today, and the world's most powerful supercomputer, Frontier HP Cray X235, can perform 1 quintillion, that's 1 followed by 18 zeros, calculations per second. To put that into perspective, the most advanced computer today is 200 trillion times more powerful than the ENIAC, and this exponential growth has happened in under a century. If computing power continues to increase at this astonishing rate, it's not hard to imagine a future where humanity, or some other advanced civilization, creates simulations so detailed, so intricate, that they would be indistinguishable from reality itself. In 2003, Oxford University philosopher Nick Bostrom published a groundbreaking paper called The Simulation Argument, in which he posited that the possibility that we are living in a simulated reality is far more likely than many might think. According to Bostrom, if a civilization reaches a level of technological advancement where it can create simulations with artificial consciousness, realistic simulations in which the entities inside the simulation believe their world to be real, then it's highly probable that we are living in such a simulation. The idea here is that, much like characters in a video game follow programmed rules and behave in predictable ways, the simulated beings within a simulation might evolve to the point where they too can think for themselves. However, even with advanced cognitive functions, these beings would never know that their reality was artificially constructed. Bostrom's argument suggests that if such a simulation were to exist, we would have no way of recognizing it, no way to perceive that we too are part of a program with our memories and perceptions being carefully curated. What's more, Bostrom's theory takes into account the rapid acceleration of technology. Since the 1940s, computing power has increased by an unfathomable amount, with no signs of slowing down. But what happens when that progress reaches an even more astonishing peak? Bostrom argues that technological development is likely to continue at an accelerated pace for the foreseeable future, and that could mean the creation of simulations that are indistinguishable from our reality. This brings us to the next point in Bostrom's argument, that technological progress will not cease, or at least, not for a long time. Historically, people assumed that the rate of technological advancement would continue its rapid trajectory indefinitely. But recently, many experts have begun to wonder if we might have already reached the limits of what current technologies can achieve. Some have pointed to Moore's law, the observation made by Gordon Moore in 1965, which suggested that the number of transistors on a microchip would double every 2 years, thus increasing the computational power of computers. For decades, this pattern held true, but recently, things have started to change. By the early 2000s, scientists began to notice that it was becoming more and more difficult to make computer chips smaller and more powerful due to physical limitations, such as heat production and energy consumption. This slowing down of progress led to widespread concerns that we might have hit a technological ceiling. However, the tech industry responded by innovating new methods, such as multi-core processors and specialized hardware. And now, we're entering a new frontier: quantum computing. Quantum computing isn't just about making computers faster. It represents a completely new way of processing information, one that operates on a fundamental level of physics that classical computers can't touch. If quantum computing becomes as ubiquitous as traditional computing is today, humanity could unlock new frontiers of knowledge and technology that we can't even fathom. But even then, there's still the question of whether we'll ever see those advancements come to fruition. As much as we dream of interplanetary civilizations and virtual realities indistinguishable from the world we know, there's always the threat that humanity might not survive long enough to witness such breakthroughs. From the looming dangers of nuclear warfare to the possibility of catastrophic natural disasters like asteroid impacts, there's always the risk that our species might not make it past the threshold of technological maturity. So what if the Mandela effect, these strange glitches in our collective memory, are more than just oddities of human cognition? What if they're actually signs of something deeper? Perhaps an indicator that we are living in a simulated reality, one where the boundaries of our memories and experiences are just as malleable as the code that underlies them. In a world where the lines between the real and the artificial are increasingly blurred, it might not be so far-fetched to consider that the world we perceive as real is in fact nothing more than a construct. However, if humanity succeeds in establishing colonies on other planets, it could dramatically alter the course of our civilization's future, potentially giving it a fighting chance to survive indefinitely. This is exactly the vision Elon Musk is working toward with his ambitious Mars mission. His goal is to create a backup plan for humanity, a safety net that would ensure our species has a future, no matter what happens to Earth. Musk has already made substantial progress, taking bold steps in the direction of space exploration and planetary colonization. Yet, there's a fascinating layer to this narrative that goes even deeper. According to philosopher Nick Bostrom, in his fourth assumption, there is a mind-bending possibility that advanced civilizations might not just aim for interplanetary survival, but also the creation of complex simulations. Imagine this. Highly advanced beings could design incredibly detailed simulations, heck, even of their own pasts. Instead of studying history through books or records, they could experience it firsthand through hyper-realistic digital recreations. Perhaps these simulations are more than historical records. They might even be used for entertainment, akin to playing an unimaginably advanced version of a video game. Here's where things get truly perplexing. What if we, ourselves, are already living inside one of these simulations? If a civilization far more technologically advanced than ours had the power to create such detailed, immersive digital worlds, we might not even be aware that we're part of one. Imagine it. If countless simulated worlds exist, the odds that we're living in the original real world, the first universe, become astronomically small. In fact, it's far more likely that we are living within one of those countless simulations. This is the premise behind the simulation hypothesis, a theory that has even some of the greatest minds in science rethinking the very nature of reality. Renowned astrophysicist Neil deGrasse Tyson has explained the idea this way. If we can accept that it is possible to create a simulation within a simulation, then the likelihood that we are part of one increases exponentially. Think about it. Even with today's technology, we can already create immersive virtual worlds, worlds that feel lifelike and tangible. Now, imagine a future where technology has progressed far beyond anything we can comprehend today. A time when we can generate entire universes, each populated with beings who, like us, believe they have free will. You could be one of these beings. You might think you're making independent choices, but what if everything you experience, all your thoughts, actions, and decisions are just part of a grand, intricately designed simulation? Now, let's take it a step further. Imagine that within the simulation, you somehow invent a computer, an advanced machine capable of running a simulation of its own. This new simulation generates yet another universe, and the cycle continues, endlessly creating layer after layer of digital worlds. If you were to randomly select a universe from this infinite series, would you be more likely to land on the one true reality, the original, or one of the countless simulations that followed it? Statistically, the odds are overwhelmingly in favor of finding a simulation, not the original world. Elon Musk has taken this theory a step further. He argues that we should actually hope we're living in a simulation. Musk's reasoning is rooted in the idea that civilizations either develop technology capable of creating hyper-realistic simulations, or they eventually face extinction. Given this, he believes it's far more likely that we are part of a simulation than living in an unaltered, original universe. Bostrom, who originally proposed the simulation hypothesis, has further refined his ideas. He suggests that the probability we are living in a simulation is incredibly high, based on a statistical argument. If advanced civilizations have the capacity to create countless simulated worlds, then by sheer numbers, it's far more probable that we are living in one of those simulations rather than the original reality. Neil deGrasse Tyson, over time, has shifted his perspective on the subject. He now proposes a fascinating possibility. If humanity has not yet developed the technology to create hyper-realistic simulations, then it means we are either living in the base reality, the original universe, or we are existing at the very end of a long chain of simulations. In this scenario, the odds are split 50-50 between being real or simulated. But proving or disproving this theory is no simple task. Philosopher David Chalmers has pointed out a critical issue. If we are indeed living in a simulation, the creators of that simulation would have the power to manipulate any evidence we uncover. This means that even if we attempt to test the validity of our reality, any results we find could be intentionally distorted, making it almost impossible to detect the truth. Shifting gears to another mind-boggling mystery, we turn to the realm of space science. There's a strange and elusive substance in the universe known as dark matter. Unlike regular matter, which we can observe through light and other forms of energy, dark matter does not interact with these forces. Yet, we know it exists because of the gravitational effects it has on galaxies and other large cosmic structures. This mystery material affects phenomena like how galaxies form and evolve, the bending of light around massive objects, a phenomenon known as gravitational lensing, and even how galaxies move in clusters. Dark matter's influence can also be seen in the shape of the universe and in the cosmic microwave background, the residual energy from the Big Bang. The most widely accepted model of the universe, known as the lambda cold dark matter, lambda CDM model, posits that only about 5% of the universe's mass and energy consists of visible, ordinary matter. Around 27% is dark matter, and a staggering 68% is dark energy. That means dark matter makes up approximately 85% of the universe's total mass, while dark matter and dark energy together account for a whopping 95% of its total energy content. Yet, despite knowing that dark matter must exist, scientists remain uncertain about its exact nature. It doesn't seem to interact with light or regular matter except through gravity, making it extraordinarily difficult to detect with current technology. Several hypotheses have emerged regarding the composition of dark matter. Some suggest it could be made up of elusive particles known as weakly interacting massive particles, WIMPs or axions. Others propose that dark matter might be composed of ancient black holes formed in the early stages of the universe's creation. Dark matter is typically categorized into cold, warm, or hot, based on how fast its particles move. Most experts agree that dark matter is cold, meaning its particles move slowly, allowing them to clump together and form structures over time. Despite the consensus that dark matter is real, a small number of researchers remain unconvinced. These scientists, puzzled by certain inconsistencies in our observations, suggest that the laws of gravity themselves might need to be adjusted. They've proposed ideas such as modified Newtonian dynamics or entirely new types of gravity. However, none of these alternative theories have been able to explain all the phenomena associated with dark matter. This means that even if gravity does need some revisions, dark matter is still likely a key player in the cosmic puzzle. The history of dark matter is rich and filled with groundbreaking discoveries that have reshaped our understanding of the universe. The tale begins in the late 1800s with the work of physicist William Thomson, better known as Lord Kelvin. In 1884, Kelvin began speculating about the number of stars near our sun. By studying the motions of stars, he wondered what would happen if there were 1 billion stars within a radius of about 3,200 light-years from the sun. The behavior of these stars would have been difficult to explain without invoking the idea of unseen material in space. Kelvin's interest in star movement set the stage for further exploration of hidden matter, and by the early 20th century, the concept of dark matter began to take shape. In 1906, French scientist Henri Poincaré introduced the term dark matter, or matière obscure, while discussing Kelvin's theories. Though Poincaré initially thought this hidden material would be much less abundant than what we could observe, his mention of dark matter marked the beginning of serious scientific consideration of the idea. The concept gained further traction in the 1920s when Dutch astronomer Jacobus Kapteyn suggested that dark matter might exist in the Milky Way. He noticed that the movement of stars was affected by invisible forces, hinting at the presence of some form of unseen mass. In 1930, Swedish scientist Knut Lundmark expanded on this idea, concluding that the universe likely contained far more mass than could be observed through telescopes. This was a revolutionary discovery, suggesting that the visible universe might only be part of the story. In 1932, another Dutch scientist, Jan Oort, added to the conversation by proposing that dark matter might be present specifically within our own galaxy, the Milky Way. Oort's work focused on the movement of stars near the galaxy's outskirts and concluded that there had to be more mass in the galaxy than was visible to our instruments. However, as time passed, the initial excitement of his discovery began to fade. The conclusions he had reached based on his calculations weren't entirely correct. He soon realized that more in-depth studies were necessary to understand the full nature of this mysterious and invisible material. The need for further research became undeniable. It wasn't until 1933 that a significant breakthrough occurred in the field, thanks to the work of a Swiss astrophysicist named Fritz Zwicky. At that time, Zwicky was conducting research on galaxy groups at the California Institute of Technology. His focus was on the Coma Cluster, a massive collection of galaxies that piqued his interest. While studying the Coma Cluster, Zwicky noticed something truly peculiar. The galaxies within this cluster were moving much faster than what could be explained by the visible matter detected with telescopes. According to the standard model of galaxy dynamics, the galaxy's speed should have been slower, given the visible mass in the cluster. This discrepancy led him to a profound conclusion. There must be a large amount of unseen mass exerting gravitational forces on these galaxies. He coined the term Dunkelmaterie, or dark matter in English, to describe this mysterious substance which he believed was responsible for the unusual speed of the galaxies. Zwicky estimated that the Coma Cluster contained about 400 times more mass than what could be detected through the visible matter alone. Although his estimate was wildly inaccurate due to the limited and outdated data available at the time, Zwicky was one of the first to propose that the universe contained unseen material that influenced the movement of galaxies through its gravitational pull. Zwicky's view on dark matter, however, differed from how we perceive it today. He envisioned dark matter as normal, ordinary matter that simply didn't emit light, not the strange, exotic substance we now associate with the term. Despite this difference in understanding, his groundbreaking work set the stage for further exploration into the nature of dark matter. As the years went by, additional evidence supporting the existence of dark matter began to emerge. One key piece of this puzzle came in 1939, when astronomer H.W. Babcock conducted a study of the Andromeda Galaxy, the closest spiral galaxy to Earth. By analyzing the motion of stars within Andromeda, he observed that the stars on the outer edges of the galaxy were moving far faster than would be expected based on the amount of visible matter present. This discrepancy suggested that the galaxy harbored far more mass than what was visible to telescopes. Initially, Babcock hypothesized that this strange rotation might be caused by light being absorbed within the galaxy or by an unfamiliar behavior of galactic motion at the outer edges. However, his findings were among the first significant clues that invisible forces, possibly dark matter, were affecting the behavior of galaxies. The very next year, in 1940, another astronomer, Jan Oort, made a breakthrough with a different galaxy. He studied NGC 3115 and detected an enormous, unseen mass cloud surrounding it. This cloud was yet another sign that galaxies might be encircled by invisible material beyond what our instruments could detect at the time. It became increasingly clear that dark matter was more than just a theory. It was an observation waiting for further confirmation. The concept of dark matter gained significant momentum in the 1970s as more discoveries reinforced the theory. One of the most influential developments came from a series of independent studies in 1974. Teams led by prominent scientists, including Jeremiah Ostraker, Jim Peebles, and Amos Yahill from Princeton University, and John Anasto and Ans Kasik from Tartu, Estonia, independently came to the same conclusion. Galaxies appeared to be surrounded by large, invisible halos of matter. This discovery was a turning point. Using both traditional optical telescopes and radio telescopes, astronomers began studying galaxies in greater detail, and the evidence for dark matter grew stronger. One of the most critical advancements came through the work of Vera Rubin and Kent Ford. By utilizing a new type of telescope, they were able to make more precise measurements of the rotational speeds of spiral galaxies. Their results were astonishing. At the same time, radio astronomers were making similar discoveries by studying atomic hydrogen at a 21 centimeter wavelength. Unlike starlight, which is concentrated in the middle of galaxies, hydrogen gas stretches much farther, allowing astronomers to examine the rotation patterns at the outer regions of galaxies. This offered a clearer picture of how much total mass a galaxy contained. In the early 1970s, astronomers using powerful telescopes such as the 300-foot Green Bank telescope and the 250-foot Jodrell Bank telescope began studying the Andromeda galaxy more closely. Their observations of hydrogen rotation curves revealed the pattern that defied the predictions made by Kepler's laws, which govern the motion of objects around a center of gravity. The hydrogen rotation curve showed that the speed of rotation did not decrease with distance from the galactic center, as one would expect. Instead, the curve remained flat, indicating that the galaxy's outer edges contained far more mass than could be accounted for by visible matter alone. In 1975, further studies by Roberts and Whitehurst measured the speed of Andromeda's rotation out to distances of 30,000 parsecs. Their findings confirmed the earlier results. The galaxy's rotation curve remained flat, suggesting the presence of a vast amount of unseen matter in the outer regions. These results marked a turning point in the understanding of dark matter. At the same time, new methods using radio telescopes working in tandem were developed, allowing astronomers to map the hydrogen rotation curves of multiple spiral galaxies. Researchers such as Rogstad and Schack in 1972 mapped the curves of 5 spiral galaxies and found that all of them exhibited flat rotation curves, further confirming the hypothesis that these galaxies contained much more mass than could be seen. By the late 1970s, the majority of astronomers had accepted the existence of dark matter halos surrounding galaxies. This realization became one of the most pressing unanswered questions in modern astronomy. Throughout the 1980s and 1990s, further studies continued to support the idea that dark matter was a fundamental component of the universe. One notable study in 1996 by Persic, Salucci, and Stell placed the final stamp of approval on the dark matter theory by analyzing nearly 1,000 spiral galaxies. Their findings provided strong, irrefutable evidence that dark matter existed. Other supporting evidence came from phenomena such as gravitational lensing, where light from distant galaxies is bent around galaxy clusters, and from the behavior of hot gas in galaxies. Tiny fluctuations in temperature detected in the cosmic microwave background, the faint radiation left over from the Big Bang, also indicated the presence of dark matter. Today, most scientists agree that dark matter consists of particles yet to be discovered, and these particles are unlike anything we've encountered in our studies of ordinary matter. The search for these elusive particles has become one of the most significant challenges in modern physics. With various experiments underway to uncover their true nature, scientists are still on the hunt for the mysterious constituents of dark matter. In simple terms, when scientists discuss matter in the universe, they refer to anything that contributes to the total energy density. As the universe expands, this matter spreads out and becomes less concentrated. This is in contrast to radiation, which fades away more quickly as the universe grows. There is, however, a special type of energy that behaves differently, the cosmological constant. Unlike matter and radiation, the energy density of the cosmological constant remains constant, no matter how much the universe expands. This unique behavior of matter, radiation, and the cosmological constant is explained by a phenomenon known as radiation redshift. Imagine the universe is expanding. As the visible universe doubles in size, the energy of particles, such as photons from the cosmic microwave background, weakens because the photons must spread out over a larger space. The same occurs with fast-moving particles like neutrinos. They lose energy as the universe expands. However, the cosmological constant, which is a part of space itself, remains unaffected by the expansion. Dark matter, in its essence, refers to parts of the universe that have mass but are invisible to current observational methods. It follows the same general principles of regular matter, exerting gravitational forces, but is made up of particles that we have yet to identify. When studying the rotation of galaxies, astronomers have observed that, unlike the planets in our solar system, the stars in spiral galaxies do not follow the expected patterns of motion. According to Kepler's third law, the farther objects are from the center of a gravitational system, the slower they should move. But in galaxies, the stars on the outer edges are often moving at the same speed or even faster than those near the center. This unexpected behavior suggests that the distribution of mass in galaxies is very different from that of our solar system. There appears to be a large amount of unseen mass, dark matter, encircling the galaxy's edges. This discovery is further supported by the application of the virial theorem, which helps explain the distribution of mass based on the movement of stars in tightly bound systems like galaxies. By studying the motion of stars in galaxies, astronomers can estimate how mass is spread out, shedding more light on the nature of dark matter. In many cases, the speeds measured in cosmic systems don't align with what we might expect based on the visible matter present. Even when we account for the intricate motions of stars, the speeds of galaxies, and other observable factors, there's a persistent discrepancy. So what's the most plausible explanation for this? The most reasonable answer, time and again, points to the presence of unseen matter, matter we cannot detect with traditional methods. This is where the concept of dark matter enters the stage. Galaxy groups in particular play a critical role in the study of dark matter. By studying these groups, we can estimate their mass through three primary methods: examining the velocities of the galaxies within the group, analyzing the X-rays emitted by the hot gas contained in the group, and investigating gravitational lensing effects. Each of these methods on its own provides valuable insights. When combined, they all point to one undeniable conclusion: dark matter is real, and it makes up about 5 times the weight of all visible matter in these cosmic clusters. One fascinating phenomenon that stems from Einstein's theory of general relativity is gravitational lensing. This effect occurs when light passes through a massive object, such as a galaxy or a cluster of galaxies, that lies between the light source and the observer. The mass of the object acts like a lens, bending the light and distorting the image of the background object. This bending doesn't depend on what the object is made of, only its mass. The heavier an object, the greater its ability to bend light. Imagine for a moment a distant quasar, one of the brightest objects in the universe. If a galaxy group sits between this quasar and us, its immense mass bends the quasar's light, warping our view. When the lensing is particularly strong, the background light can be distorted into arc-like shapes. This strong lensing has been observed in many distant galaxy groups, including one famously known as Abell 1689. By studying the shape of these arcs, scientists can work out the mass of the galaxy group causing the lensing effect. But what about weaker lensing? In these cases, the bending is subtler. Instead of dramatic arcs, we observe slight distortions in the shapes of galaxies. Although these changes are smaller, they still offer a wealth of information about the distribution of dark matter in the universe. These subtle distortions fit perfectly with predictions based on dark matter, allowing scientists to map out the unseen matter that permeates space. Dark matter behaves in stark contrast to regular matter. While normal matter interacts strongly with light, enabling it to be detected and studied, dark matter remains invisible to light, making it far more elusive. Nevertheless, dark matter's gravitational influence is undeniable. For example, it affects the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB provides a snapshot of the early universe, and within its almost uniform temperature, there are tiny temperature fluctuations called anisotropies that reveal much about the nature of the universe. These fluctuations are minuscule, about 1 part in 100,000, but by carefully mapping and analyzing them, scientists can learn about the structure of the universe and the forces that shaped it. The pattern of these temperature variations, when plotted as a graph known as the angular power spectrum, displays peaks that are evenly spaced but vary in height. These peaks hold vital information about cosmological parameters, including the amount and distribution of dark matter. The first hint of these temperature fluctuations came from the COBE satellite in 1992. However, the resolution was not high enough to discern detailed features. It wasn't until the Boomerang experiment in 2000 that the first distinct peak was observed. Later, more precise measurements by the WMA and Planck satellites gave a clearer view of these fluctuations, strengthening our understanding of the universe's fundamental structure. These observations supported the lambda cold dark matter, lambda CDM model of cosmology, the most widely accepted framework for understanding the formation and evolution of the cosmos. The universe, just after the Big Bang, was a smooth and homogeneous place. But small fluctuations in density existed, and over time, these tiny differences grew, eventually collapsing into the stars, galaxies, and clusters of galaxies that we see today. But this process didn't happen by chance. In the early universe, radiation dominated and prevented normal matter from clumping together. This meant that, without any help, these small fluctuations would not have had enough time to form the massive structures we observe now. Enter dark matter. Unlike normal matter, dark matter doesn't interact with radiation, allowing density fluctuations to grow over time. These growing fluctuations, or gravitational wells, eventually pulled in normal matter, accelerating the formation of galaxies and other cosmic structures. Dark matter acted like a magnet, drawing in regular matter and helping to build the universe we see today. A striking example of dark matter's role comes from the Bullet Cluster, an extraordinary collision of two massive galaxy clusters. What makes the Bullet Cluster so remarkable is the apparent separation between the distribution of mass, as inferred from gravitational lensing, and the location of visible matter. In this case, the visible gas, which interacts with light and radiation, was slowed down by electromagnetic forces during the collision. On the other hand, dark matter, which doesn't interact with light in the same way, passed through the collision unharmed, leaving two distinct lensing peaks behind. This phenomenon is a powerful piece of evidence supporting the existence of dark matter. In addition to gravitational lensing, astronomers also use Type Ia supernovae as standard candles to measure distances across the universe. Since these supernovae have a known brightness, comparing their actual brightness to how dim they appear allows scientists to estimate their distance. This method revealed an astounding discovery. The universe is not only expanding, but doing so at an accelerating rate. This observation is often associated with dark energy, another mysterious component of the universe that we are still working to understand. Another crucial piece of the cosmic puzzle lies in the study of baryon acoustic oscillations, BAO. These are regular patterns in the density of normal matter, specifically baryons, that occurred early in the universe before atoms had formed. Sound waves rippled through the hot, dense plasma of photons and baryons, creating density variations that we can still observe today in the cosmic microwave background. As the universe expanded, both dark matter and regular matter began clumping together. However, the early sound wave patterns left behind subtle imprints that scientists can still trace. By studying these BAO imprints and combining them with CMB measurements, scientists can refine our understanding of the universe's expansion, the distribution of matter, and other key cosmological parameters. In particular, these studies support the Lambda CDM model and offer invaluable insights into the amount and distribution of dark matter throughout the cosmos. Large surveys, such as the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey, have helped map out the three-dimensional structure of the universe. These surveys measure the redshift of galaxies, how the light from distant objects shifts toward the red end of the spectrum due to the expansion of the universe. However, these measurements are not perfect. The redshift we observe is influenced by both the expansion of the universe and the peculiar motion of individual galaxies. This leads to some interesting effects. Superclusters, which are vast collections of galaxies, tend to grow more slowly than the universe as a whole, as their gravity pulls things together. Meanwhile, the vast empty spaces between galaxies, known as voids, are expanding faster than the universe itself. This differential movement creates distortions in the way galaxies appear to move. For instance, galaxies in front of a supercluster seem to be moving faster toward it, resulting in a higher redshift. Conversely, galaxies behind a supercluster appear to be moving more slowly, causing a lower redshift. This difference in movement distorts the appearance of superclusters, making them look flattened along our line of sight, while voids appear stretched. These observations are a testament to the complexity and beauty of the universe, where the interplay between visible matter, and dark energy shapes the very fabric of space itself. In the realm of cosmic research, certain phenomena, such as the intricate patterns formed by galaxies and cosmic structures, are incredibly difficult to observe directly in individual objects. This is because the true shape of a single structure is often hidden from us. Instead, scientists have relied on a more practical approach, averaging data from a multitude of these structures. Through this method, they noticed a consistent pattern that had been first predicted by the physicist Nick Kaiser in 1987. It wasn't until 2001, however, that the findings were confirmed with remarkable precision by the 2DF Galaxy Redshift Survey. The results from this survey mirrored the predictions made by the Lambda Cold Dark Matter, Lambda CDM model, a framework that has become one of the cornerstones of modern cosmology. In a related field of study, the Lyman Alpha Forest offers another fascinating glimpse into the universe's hidden workings. The Lyman Alpha Forest is not a physical object, but rather a series of absorption lines seen in the light emitted by distant galaxies and quasars. These lines are caused by neutral hydrogen atoms absorbing light at a very specific wavelength known as the Lyman alpha transition. By carefully studying these absorption lines, astronomers are able to test and refine their cosmic models. The data obtained from these observations often aligns with results from other major cosmological surveys, including those derived from the WMAP data, providing a deeper understanding of the universe's early conditions. One of the key concepts in understanding the structure of the universe is dark matter, an enigmatic substance that makes up a significant portion of the cosmos. Dark matter is divided into three broad categories: cold, warm, and hot. These classifications don't refer to temperature in the conventional sense. Rather, they describe the speed at which dark matter particles moved during the early universe. The idea is simple but profound. These categories reflect how far dark matter particles could travel due to their random motion before the universe's rapid expansion slowed them down. The term free streaming length, FSL, is used to define the distance a particle could travel before the expansion of the universe prevented it from traveling further. Cold dark matter is made up of particles with a small FSL, meaning they didn't move very far before the universe expanded. These slow-moving particles were key in forming the first small structures in the cosmos. On the other hand, hot dark matter, with its large FSL, would have traveled vast distances, preventing smaller structures like galaxies from forming. Instead, it would have led to the creation of massive structures like superclusters, which would later break apart into galaxies. Observations of deep space, particularly the early formation of galaxies, support the idea that the universe's structure began with smaller formations, with galaxies emerging first, followed by groups of galaxies and finally larger cosmic structures. This sequence aligns with the notion that most dark matter is cold and slow-moving. Interestingly, the idea that fast-moving particles like neutrinos could make up a large portion of dark matter is now largely ruled out. Neutrinos, being incredibly fast, would have moved too quickly to allow the formation of the smaller structures that we observe in the universe today. This highlights the crucial role that slow-moving dark matter plays in shaping the universe's structure. While dark matter is famously invisible, it isn't some entirely foreign substance. In fact, many of the objects that astronomers have studied, such as planets, brown dwarfs, small stars, and even black holes, could technically be part of this dark matter category. These objects, known as MACOs, massive compact halo objects, behave similarly to dark matter in that they exert gravitational forces but are difficult to detect directly. For a time, scientists thought MACOs might make up a large portion of dark matter. However, this hypothesis has largely been dismissed due to a wealth of observational data. One of the most compelling pieces of evidence against the MACO hypothesis is that if regular matter were abundant in the universe, we would be able to see it through its interactions with light. When starlight passes through such matter, it would illuminate or scatter in ways that would be visible to us. Yet, no such signals have been observed in the quantities necessary to account for dark matter. Moreover, the Big Bang Theory, which explains the formation of elements in the early universe, predicts that if regular matter were prevalent, we would detect higher amounts of elements like helium and lithium. However, observations reveal that only about 4 to 5% of the universe's total mass is made of the ordinary matter that we can detect. Further studies have shown that only a small fraction of dark matter seems to be made of regular objects like small planets or black holes. Research on gravitational microlensing, the phenomenon where light bends around massive objects, suggests that these MACOs cannot account for the majority of dark matter. In fact, their sizes are inconsistent with the mass required to account for the total amount of dark matter. Perhaps the most groundbreaking evidence comes from the study of the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. Observations from missions like WMAP and Planck provide strong proof that approximately 85% of the matter in the universe is dark matter, which interacts weakly with light and regular matter, if at all. This supports the hypothesis that dark matter is largely invisible, detectable only through its gravitational influence on surrounding matter. If dark matter isn't made of ordinary matter, then it must be composed of something else, something referred to as non-baryonic matter. This could consist of exotic particles that don't interact with light in the same way as the particles that make up ordinary matter. These particles didn't contribute to the formation of the elements during the Big Bang, a process known as Big Bang nucleosynthesis. Instead, their presence was revealed only through their gravitational effects, such as bending light in a process called weak gravitational lensing. There are two primary possibilities for what dark matter might consist of. Unknown particles and very old black holes formed in the universe's early days. Unlike regular matter, these unknown particles would not have played a role in the creation of elements following the Big Bang. Instead, they would have only been detectable due to their gravitational effects on other objects. Some of these dark matter particles might even interact with one another, leading to a type of dark matter known as self-interacting dark matter. Additionally, some theories suggest that dark matter could interact with regular particles, such as weakly interacting massive particles, WIMPs, which could lead to detectable signals like gamma rays, neutrinos, and cosmic rays. WIMPs are among the most promising candidates for dark matter. These hypothetical particles are extremely small and interact only through gravity and perhaps the weak nuclear force. Many theories suggest that WIMPs were created in the early universe just like regular particles, and they could form the basis of cold dark matter. To explain the current abundance of dark matter, WIMPs would need to annihilate each other in specific ways, a process that aligns with the properties of particles with masses around 100 billion electron volts. This idea, often referred to as the WIMP miracle, fits remarkably well with theories that extend the standard model of particle physics. In an effort to detect these elusive particles, scientists are conducting experiments in laboratories and large particle accelerators, like the Large Hadron Collider, in hopes of creating WIMPs or detecting the byproducts of their annihilation. They are also looking for indirect signs of dark matter, such as gamma rays or neutrinos, that might be produced when dark matter particles collide or decay. Despite the challenges, the search for dark matter continues to be one of the most exciting and crucial endeavors in modern astrophysics. In the early 2010s, experiments failed to provide strong evidence for the existence of dark matter particles, and results from particle colliders, such as those at CERN, raised serious doubts about the most straightforward dark matter theories, including the notion of weakly interacting massive particles, or WIMPs. These particles had been widely proposed as a solution to the dark matter puzzle, but despite intense searching, they remained elusive. One alternative that has gained considerable attention over the years is the axion, a hypothetical particle first introduced in 1978 by physicists Frank Wilczek and Steven Weinberg. The axion was initially suggested as a way to address a problem in the theory of how fundamental particles like quarks and gluons interact. In essence, it was an effort to explain why certain symmetry properties of the strong nuclear force seem to hold up under observation, a conundrum that needed resolution. Axions are extremely light, and their interactions with other particles are incredibly rare. This makes them a strong contender for dark matter. Unlike heavier particles, which interact via multiple forces, axions barely interact with matter, making them undetectable by conventional means. Theoretically, they could have been produced in the early universe and might still be present today. Depending on their mass, axions could even explain some of the unresolved issues in the lambda cold dark matter, lambda CDM model, the leading cosmological framework. As the search for WIMPs continues to turn up empty, the axion theory has gained favor, with researchers exploring how these elusive particles could solve some of the small-scale mysteries associated with dark matter. Another fascinating possibility is the idea that dark matter could be composed of primordial black holes, ancient black holes that might have formed in the moments following the Big Bang. During the period of rapid expansion, known as inflation, regions of the universe that were especially dense might have collapsed under their own gravity, forming black holes without the need for a dying star, as is the case for the black holes that form in more familiar ways. These primordial black holes could range in size from as small as an atom to several times more massive than typical black holes created from collapsing stars. The concept of primordial black holes as a potential source of dark matter was first proposed in 1967 by physicists Yakov Zeldovich and Igor Novikov. Later, Stephen Hawking revisited this idea in 1971, helping popularize it. Black holes, after all, are well understood within the framework of general relativity, and their existence is confirmed by observational evidence. This made them an attractive candidate for dark matter. If primordial black holes could exist in the early universe, they might account for a large portion of the universe's missing mass. However, forming these tiny black holes would require very special conditions, potentially involving exotic aspects of cosmic expansion or mechanisms beyond standard particle physics. In 2015, the detection of gravitational waves from black holes merging brought renewed interest to the possibility that primordial black holes might contribute to dark matter. Some of the black holes detected during these events were heavier than would be expected from the normal processes of stellar collapse, which raised speculation that they could be relics from the early universe. But subsequent research, which looked for signs of gravitational lensing, a phenomenon where light is bent by massive objects, failed to find definitive evidence for these black holes. Some scientists suggest this could be due to incorrect assumptions about the black holes' sizes, and they remain open to the possibility that these ancient black holes still exist, though their detection remains elusive. Despite this, data from the Voyager 1 spacecraft, which traveled beyond the influence of the Sun, presented a surprising twist. Voyager 1 measured the flow of small charged particles and found fewer than expected, with energy levels that did not align with existing predictions. This led some researchers to propose that tiny black holes might be too rare to account for dark matter. Nevertheless, the idea of primordial black holes continues to spark scientific interest, and theories of dense dark matter are still being explored. The mystery of dark matter remains unsolved as of 2018. More recent studies, such as those examining the Andromeda galaxy, have shown no signs of gravitational lensing that would suggest the presence of small black holes. This adds further uncertainty to the hypothesis of primordial black holes. However, there is still a gap in our observational capabilities, especially in the size range where tiny black holes could exist and potentially make up dark matter. This remains an active area of research, one that challenges our understanding of the universe at a fundamental level. If dark matter is indeed composed of particles that interact only weakly with ordinary matter, another key question arises. Could these particles coalesce to form larger objects like planets, stars, or black holes? Traditionally, scientists have answered this question with a resounding no. There are two main reasons for this: the inability of dark matter particles to lose energy and the limited ways in which they interact with other forms of matter. In normal matter, particles lose energy through various processes. For example, as particles move toward the center of gravity, they slow down, releasing energy and allowing them to gather into more complex structures like stars and planets. Dark matter particles, however, do not seem to have any mechanism to lose energy in the same way. They interact primarily through gravity and perhaps weakly via other unknown forces, but not in the complex ways that normal matter does. This lack of interaction means that dark matter particles, when pulled toward a gravitational source, would simply speed up as they heated up, making it nearly impossible for them to form dense objects like stars or planets. For normal matter, interactions through gravity, electromagnetism, and the strong nuclear force allow for the creation of intricate structures like atoms, galaxies, and stars. For instance, inside stars, particles undergo nuclear reactions, generating light and releasing particles such as neutrinos. Dark matter, by contrast, seems to only interact via gravity, making it unlikely to form the kind of complex objects that we see in the visible universe. This raises a critical question. If dark matter is made up of subatomic particles, could they pass through every square centimeter of Earth millions or even billions of times each second without leaving a trace? While this idea might seem far-fetched, it forms the basis of many ongoing experiments. One of the most prominent theories currently being studied is that dark matter could consist of weakly interacting massive particles, 1-imps. But axions are also a serious area of research. Several projects, like the Axion Dark Matter experiment, are dedicated to uncovering the nature of these elusive particles. Dark matter research also includes two primary experimental approaches: direct detection and indirect detection. Direct detection experiments are designed to observe rare interactions between dark matter particles and atoms within specialized detectors. The goal is to detect tiny energy changes, typically on the order of a few thousandths of an electron volt, that result from these interactions. For example, if a dark matter particle collides with an atom, the atom might release energy in the form of light or vibrations, which can then be measured. To minimize interference from background noise, these experiments are often conducted deep underground, in locations such as the Stawell Mine in Australia, the Sudan Mine in Africa, and the Gran Sasso National Laboratory in Italy. Some well-known experiments that utilize these techniques include CDMS, cryogenic dark matter search, CREST, xenon, and LUX, large underground xenon. These experiments are adept at distinguishing between signals from dark matter and those generated by other particles, given that dark matter is expected to interact differently with ordinary matter. Indirect detection experiments, on the other hand, focus on identifying the byproducts of dark matter particles that might be annihilating or decaying into other particles. While direct evidence of dark matter has not yet been observed in these experiments, they have helped narrow down potential explanations for the nature of dark matter. One intriguing observation from projects like DAMA and Libra is a yearly fluctuation in their data, which some scientists speculate might be due to Earth passing through a cloud of dark matter as it orbits the Sun. The search for dark matter remains one of the most exciting frontiers of modern science, as it holds the key to understanding the true nature of the universe and the elusive mass that shapes its structure. As technology advances and our ability to probe deeper into the cosmos increases, the mysteries surrounding dark matter may eventually be unlocked, offering profound insights into the workings of the universe itself. However, some experiments, such as LUX and Super CDMS, have failed to replicate the expected results, casting doubt on the initial findings. This discrepancy has led to uncertainty in the claims about the detection of dark matter. The challenges of pinpointing the elusive particles continue as many researchers turn to alternative methods to track the movement of dark matter itself. One approach looks at how the solar system moves through the galaxy. Experiments like DMPC and DRIFT aim to detect shifts in the direction of dark matter's motion, a key effort in distinguishing real signals from background noise. These experiments work by focusing on cosmic movements and patterns that might reveal hidden clues about dark matter's behavior. Indirect detection methods are also being utilized to uncover dark matter. These methods look for unusual signals from areas of space thought to harbor large concentrations of dark matter, such as the center of the Milky Way. In this region, if two dark matter particles were to collide, the event might result in their annihilation, releasing high-energy light or even pairs of regular and antimatter particles. The potential discovery of such signals would lend weight to the theory that dark matter could be composed of weakly interacting massive particles, WIMPs. If dark matter particles are unstable, they may slowly break down into ordinary particles, which could be detected as bursts of gamma rays, antimatter, or high-energy cosmic particles. The challenge, however, is that similar signals can be produced by other space phenomena, like supernova or cosmic rays. Multiple independent detections are therefore required to confirm the presence of dark matter with certainty. Another intriguing possibility is that dark matter particles could become trapped inside stars or planets, where they could collide with one another, producing high-energy neutrinos. These neutrinos might be detected on Earth as bursts of energy. Such findings would offer strong evidence supporting the idea that dark matter is composed of WIMPs. Leading experiments such as Amanda, IceCube, and Antares are actively looking for these elusive neutrino signals. In 2015, the groundbreaking discovery of gravitational waves by the LIGO Observatory opened new doors to studying dark matter. Particularly intriguing is the idea that some of the dark matter in the universe could exist in the form of primordial black holes, objects so small and dense that they are difficult to detect by conventional means. Researchers are now investigating whether these tiny black holes might be playing a role in the dark matter puzzle. The search for dark matter signals extends beyond telescopes and particle detectors. For instance, in 2008, the Energetic Gamma Ray Experiment Telescope, EGRET, detected a surprising surge in gamma rays emanating from the Milky Way. While some scientists initially believed this was due to errors in the telescope's sensitivity, further data collection suggested the possibility of an unknown source, such as dark matter or an unexplored group of stars. In 2009, the Fermi Gamma Ray Space Telescope recorded an unexpected increase in gamma rays from the Milky Way center, again raising the question of whether dark matter was responsible. Some speculated that this surge could be caused by a new type of star cluster, but dark matter remained a potential explanation. Further observations in 2012, as part of the Fermi mission, revealed a 130 billion electron-volt signal that seemed to originate from the center of the galaxy. Some researchers hypothesized that this could be a direct indicator of dark matter, potentially suggesting that dark matter could be decaying into gamma rays. Meanwhile, ground-based telescopes have focused their efforts on smaller galaxies and galaxy clusters, looking for any anomalies that might point to the presence of dark matter. In 2006, the Pamela experiment detected an unusually high number of positrons, particles that are the antimatter counterparts of electrons. This was considered another potential signature of dark matter, though no corresponding rise in antiprotons, another possible byproduct, was observed. In 2013, the Alpha Magnetic Spectrometer, AMS, which was mounted on the International Space Station, recorded high-energy cosmic rays that might also be linked to dark matter interactions. Beyond cosmic observations, another avenue for discovering dark matter involves recreating it in laboratories on Earth. Scientists at the Large Hadron Collider, LHC, have been actively searching for dark matter particles that may form during proton collisions. Since dark matter interacts very weakly with ordinary matter, it would be detectable through an imbalance in energy and momentum during these high-energy collisions. The LEP, Large Electron Positron Collider experiment, has also explored potential dark matter interactions with electrons. Yet, even if dark matter were detected in these experiments, it would need to be further confirmed through direct or indirect detection methods, as its nature remains unidentified. The search for dark matter is far from straightforward. Some scientists have proposed alternative theories, such as modifying the laws of gravity itself in place of invoking dark matter. Concepts like modified Newtonian dynamics, M-on-D, negative mass, and dark fluid are all part of the conversation. These theories aim to explain the phenomena attributed to dark matter without requiring the existence of such elusive particles. However, the prevailing consensus among most scientists is that dark matter is real, largely due to the many ways its effects can be observed in the universe. Despite decades of research and many competing theories, dark matter continues to elude our grasp. It is an enigma, whose presence is woven in the very fabric of the cosmos, yet whose form remains one of the greatest mysteries in modern physics. As we look to the stars, one such mystery takes shape in a star system nestled in the Centaurus constellation, a vast region of space that houses the well-known Alpha Centauri system. This system, which includes 3 stars, is familiar to many, but there is one object hidden among them that stands out as a true anomaly: the bizarre and perplexing Chabille star. Chabille star, scientifically known as HD 10165, is an extraordinary celestial body. Located 365 light-years away from Earth, this massive star weighs 4 times the mass of our Sun. Most stars undergo thermonuclear fusion, where lighter elements like hydrogen are fused into heavier elements such as helium. This process generates the energy that powers stars. However, Chabille star seems to defy this norm. Rather than producing the expected elements, Chabille star creates materials that scientists never anticipated finding in such an environment. Some of these elements are so unusual that they may not even exist in nature, or at least not yet. The star has earned the nickname plutonium star due to its apparent production of large quantities of plutonium and other incredibly heavy, unstable elements. The presence of plutonium and similar elements in Chabille star is baffling, as these substances are highly unstable and decay rapidly. Plutonium, for example, has a half-life of only 24,000 years, an incredibly short time span in comparison to the lifespan of a star. Such elements should not exist in a star for long, yet they appear to persist within Chabille star. To investigate the star's strange behavior, astronomers analyze the light emitted by stars. By examining the star's spectrum, its chemical fingerprint, scientists can determine what elements are present. However, when they looked at Chabille star's spectral signature, they were met with a chaotic and disordered pattern that defied analysis. It was as if the star was emitting an infinite number of spectral lines, making it nearly impossible to draw conclusions about its composition. Despite decades of observation since the 1960s, astronomers have yet to determine exactly what Chabille star is made of. Some theories suggest that the star contains elements that have yet to be discovered by science, substances that exist only within this singular, mysterious celestial body. One of the most puzzling aspects of Chabille star is its almost complete lack of iron, an element that is common in most stars. Iron is a byproduct of stellar fusion, and its absence in this star hints that something entirely different is happening inside. The star's spectrum, rich in lanthanides, rare and heavy elements, further suggests that Chabille star operates in an entirely unusual way. Elements like europium and samarium are found in abundance, though they typically exist only in trace amounts within other stars. Even more perplexing, astronomers have detected the presence of promethium and plutonium in the star. These elements, which decay rapidly, should not exist in such quantities within a star, particularly one that has lasted as long as Chabille star has. Their existence challenges everything we know about stellar evolution. Scientists have proposed several potential explanations for this anomaly. Some suggest that the elements could have been created during a nearby supernova, with the resulting debris forming part of Chabille star. This would explain the unusual presence of materials that should not naturally occur in such a setting. However, no theory has yet offered a fully satisfying explanation for this extraordinary celestial object. HD 10165, a star that has captured the attention of astronomers around the world, remains an enigma. Despite various theories attempting to explain its peculiar characteristics, there is little concrete evidence to confirm any of the hypotheses. Some scientists believe that the star's unusual features might be the result of neutron-star interactions, suggesting that a nearby neutron star could be triggering nuclear reactions inside the star, specifically in its Chabille region. This interaction might be responsible for the creation of new elements. However, the star is not located near any known neutron stars, rendering this theory less plausible. Another intriguing theory suggests the presence of undiscovered super-heavy elements inside HD 10165. These hypothetical elements, which scientists have only managed to synthesize in microscopic amounts in laboratories, could be breaking down into more familiar, short-lived isotopes. This breakdown might explain the traces of plutonium and promethium observed in the star's chemical signature. Elements like flerovium, ununennium, and unbenylium, substances that remain theoretical and have yet to be confirmed in nature, might exist naturally in this star. If these elements are indeed present, it would challenge our understanding of chemistry and nuclear physics and could redefine what we know about the universe. Further expanding on this theory, another possibility is that HD 10165 could be a part of the so-called island of stability. This is a theoretical group of super heavy elements that are remarkably stable compared to other elements which decay quickly. Despite years of searching, scientists have yet to find any trace of these stable elements. If HD 165 is indeed part of this mysterious island, it would be a groundbreaking discovery, offering profound insights into the stability of heavy elements and the nature of the atomic nucleus. But the star's strange properties do not end with its chemical composition. The star's motion through space is also highly irregular. Most stars follow predictable, well-established paths as they orbit the galactic center. Yet, HD 165 seems to defy these norms, moving along an unexplained trajectory. Some researchers speculate that an unknown force may be acting on the star, though there is no definitive evidence to confirm this theory. This abnormal motion only adds another layer of mystery to the star's already bizarre behavior. In light of the many unexplained characteristics of HD 165, a controversial and fascinating theory has emerged. Could extraterrestrial civilizations be involved? The idea that alien technology might be responsible for the star's peculiarities was first proposed in 1980 by American scientists Daniel Whittem and Jason Wright. They suggested that advanced extraterrestrial civilizations might use stars like HD 10165 to dispose of their nuclear waste. According to this theory, the presence of certain short-lived elements could be a byproduct of alien technology. While this remains a highly speculative idea, it has sparked a long-running debate in the scientific community. If this star is not the result of alien activity, understanding its chemical makeup and the mysteries surrounding its behavior could still have revolutionary implications for astrophysics. One such theory posits that a nearby neutron star might be influencing HD 1165, altering its atmosphere and giving rise to its unusual features. However, the absence of neutron stars in the vicinity of HD 110165 casts doubt on this explanation. Alternatively, scientists from the University of South Wales propose that the actinides detected in the star might be the result of the slow decay of superheavy elements. This theory is tied to the concept of the island of stability, a theoretical group of elements with more than 114 protons, which might be stable enough to exist for longer periods and break down into elements like plutonium and Einsteinium. If true, this could mean that HD 110165 is home to an entirely new isotope, one that exists naturally in the universe but has yet to be discovered. The sheer oddity of this star is undeniable, and it serves as a reminder that the universe still holds countless secrets, many of which remain beyond our grasp. While researchers continue to study HD 110165, we may never fully understand its origins, chemical composition, or behavior. Perhaps one day, the mysteries surrounding this star will be unraveled. Or perhaps, in a far more speculative turn of events, an advanced civilization will someday send someone back in time to reveal the true nature of HD 1165, bridging the gap between science and science fiction. Time travel in itself remains one of the most mind-bending concepts in both science fiction and science. The idea of traveling back in time to alter the past raises a number of paradoxes that challenge our understanding of reality. One of the most famous of these is the grandfather paradox. Imagine that you travel back in time to prevent your grandparents from meeting, thereby erasing your existence. But if you were never born, how could you have traveled back in time in the first place? This paradox suggests that any attempt to alter history would result in a logical contradiction, leaving us to question whether time travel is even possible. Some theorists suggest that history would somehow correct itself, ensuring that events unfold in such a way that you are still born, no matter what you do. Others propose that time travel might create parallel universes, where an alternate version of you exists in a different timeline, and history continues as if unchanged. This raises another paradox, the predestination paradox. In this scenario, you might travel back in time with the intent to stop a tragic event, only to inadvertently cause it. For instance, if you attempt to prevent a car accident, you might accidentally cause it, thereby ensuring the tragedy still happens. This paradox suggests that certain events in history are destined to occur, no matter how much we try to intervene. Even more perplexing is the bootstrap paradox. This paradox involves the concept of an object or piece of information existing without a clear point of origin. Imagine traveling back in time, giving someone a piece of knowledge, and later discovering that you had only learned that knowledge because you had given it to them in the past. This creates a loop of events with no beginning or end, leaving us to question the nature of causality itself. The bootstrap paradox challenges our understanding of how time and events are interconnected, suggesting that certain things might exist without a clear origin. These paradoxes, including the grandfather paradox, the predestination paradox, and the bootstrap paradox, highlight the complexities and contradictions that time travel presents. If time travel were possible, the consequences of altering the past might be far more profound and mysterious than we can imagine. Some theories, like the many worlds interpretation, propose that changing the past could create alternate timelines, while others suggest that time itself would prevent paradoxes from occurring by correcting any changes. But what if we could travel into the past and alter events without causing paradoxes? Would that be the key to understanding the true nature of time? Time travel is a theme that has fascinated writers, philosophers, and scientists alike. The concept appears in many works of science fiction, most notably in Robert Heinlein's short story All You Zombies, which explores the paradoxes inherent in time travel. Films like Terminator 2 have popularized these ideas, making them accessible to a wide audience. These paradoxes, which challenge our understanding of existence and reality, continue to puzzle both scientists and enthusiasts. The work of physicists like Kip Thorne, who explored the possibility of closed time-like curves through wormholes, has even suggested that time travel could, in theory, be consistent with the laws of physics. Yet as of now, it remains a concept far beyond our reach. The mysteries of time travel may one day be unraveled, or perhaps they will remain as one of the greatest paradoxes of the universe. However, the challenges posed by time travel paradoxes become even more intriguing when they intersect with experimental physics. One notable illustration of this is Joseph Pinsky's time paradox. Joseph Pinsky, an American theoretical physicist, conceived a scenario that is as elegant as it is perplexing. He imagined a billiard ball being fired into a curved wormhole. To understand the significance of this, it is important to grasp what a wormhole represents. A wormhole is a theoretical construct in physics, a tunnel-like structure connecting two separate points in spacetime, potentially allowing travel between them. In Pinsky's thought experiment, this curved wormhole functions as a kind of temporal gateway. Its entry and exit points are physically close, yet they exist at different moments in time. Consequently, the ball emerges from the wormhole in the past, just in time to collide with its younger self, diverting it so that it never enters the portal. This paradox, while seemingly simple, provides a profound lens through which to examine the convoluted issues surrounding time travel, particularly on a macroscopic scale. Pinsky deliberately sidesteps the more contentious philosophical debates about free will, the grandfather paradox, or quantum superposition, each of which tends to complicate the analysis of temporal phenomena. Instead, his approach is rooted firmly in classical mechanics and the laws of motion, offering a solid and approachable foundation for the exploration of temporal anomalies. Physicists have taken this speculative paradox seriously. For instance, Kip Thorne, a highly respected scientist, examines it in his seminal work, Black Holes and Time Warps. Thorne and his colleagues analyzed the various potential outcomes of Pinsky's experiment, concluding that although the results might differ with each trial, there is a notable likelihood that the ball will emerge from the wormhole in a manner that does not prevent it from entering the portal. This insight subtly echoes the broader conclusions of time travel theory, where in many scenarios, the universe appears to resist changes that would drastically alter established events, a concept reminiscent of the grandfather paradox. While Pinsky's paradox does not assert that destiny is predetermined, it aligns closely with Thorne's theoretical framework, helping scientists navigate some of the perplexing questions that arise when contemplating time travel. And yet the curiosity of humanity is not confined merely to the study of temporal mechanics. It extends far into the cosmos, driven by the age-old question of whether we are alone in the universe. For decades, humans have scanned the vast expanse of space in search of even the faintest indication that intelligent life exists beyond Earth. Equipped with increasingly sophisticated telescopes, scientists and enthusiasts alike have observed stars, galaxies, and distant planets, hearts pounding with the hope of detecting a signal that might confirm we are not solitary in the universe. For the most part, these efforts have been met with what has been called the eerie silence of the cosmos, broken only by the distant hum of pulsars or the faint static of the cosmic microwave background. Then, on August 15th, 1977, a remarkable event disrupted that silence. For the first time in history, a radio signal unlike any previously encountered was detected. It was sharp, intense, and appeared as a deliberate transmission from beyond our planet, a signal that seemed to carry intelligence. Dr. Jerry Eman, working with the Big Ear Radio Telescope team, was so struck by the anomaly that he circled the signal on the printout in red pen and, without hesitation, wrote the now famous exclamation, "Wow!" That simple reaction would come to define one of the most intriguing mysteries in the search for extraterrestrial intelligence, giving the signal its enduring moniker, the WOW signal. This enigmatic event has captivated scientists, dreamers, and space enthusiasts for nearly 5 decades. Its brief yet powerful appearance continues to provoke speculation and debate. Could it have been a message from an alien civilization or merely a quirk of the cosmos? At the time, the Search for Extraterrestrial Intelligence SETI program, funded by NASA, was in full operation, dedicated to scanning the heavens for signs of intelligent life. For months, the Big Ear telescope at Ohio State University had monitored the cosmic static, listening for anomalies amidst the endless white noise of the universe. Then, on that historic night, the silence was shattered. Dr. Eman, on the night shift, observed a sudden, intense burst of radio waves, 30 times stronger than anything the telescope had previously recorded. It was unlike any terrestrial signal, perfectly fitting the theoretical parameters that suggested a source beyond Earth. The origin of the WOW signal was traced to a region within the Sagittarius constellation, a thoroughly studied segment of the sky. Its extraterrestrial provenance was indisputable, and yet, despite decades of follow-up observations and scrutiny, the signal has never repeated. This singular event represents both the tantalizing promise and the frustrating elusiveness of the search for extraterrestrial intelligence. It exemplifies humanity's enduring fascination with the unknown, the drive to seek answers to questions as old as our species. Are we alone? Have we already glimpsed the first whispers of another civilization? The WOW signal remains a powerful reminder of the mysteries that stretch across space and time, urging us to continue probing the universe with unrelenting curiosity and wonder. However, despite the excitement and anticipation surrounding this extraordinary discovery, the true nature of the signal remained an elusive mystery. Was it perhaps a communication from an advanced alien civilization reaching out to us across the vast stretches of space? Or could it have been a mere fluke, an inexplicable burst of radiation from some unknown cosmic phenomenon, a fleeting anomaly with no deeper significance? These questions have puzzled scientists and enthusiasts alike for decades. The signal itself, unfortunately, left behind no tangible evidence of its origin or intent. The Big Ear Radio Telescope, the instrument responsible for capturing it, did not record any sounds in the conventional sense. Its primary function was not to capture voices or messages, but to measure the strength of radio waves, a vital task in the pursuit of knowledge about the universe. The data Dr. Eman circled on his printout consisted of numbers, each one representing the intensity of the signal's strength, encoded by the telescope in a system designed to quantify the radio waves it detected. At that time, most of the signals Big Ear had encountered were faint, weak, almost indistinguishable against the constant hum of cosmic background noise. The numbers typically ranged between 1 and 3 on the scale. But the WOW signal was different. It was so incredibly intense that the scale could not even accommodate its full magnitude. The radio waves from this signal were off the charts, prompting researchers to mark the data with a combination of letters and numbers that reflected its extraordinary power. This marked the WOW signal as an anomaly, one of the most significant events in the history of radio astronomy. What made the WOW signal even more intriguing was its lack of an accompanying audible sound. There was no voice, no discernible language, just a sharp burst of radio waves. Unlike the familiar broadcasts or signals that carry clear, structured information, the WOW signal stood out like a solitary flare against the endless sea of cosmic noise. The data collected by the Big Ear radio telescope didn't contain a coherent message. It was simply a spike in intensity, a blip that caught the attention of astronomers worldwide. Despite this, the event was momentous. It was the first time a signal of such strength had been detected by humanity. A powerful radio wave that stood apart from the usual interference and noise. It fit the precise characteristics that scientists had been searching for in their quest to detect extraterrestrial intelligence, one of the great mysteries of modern science. And yet, the signal did not offer a clear explanation of its origin, which only fueled further speculation. Over the years, the WOW signal has been the subject of numerous theories, each one seeking to explain its origin. Some propose that it could have been an intentional transmission from an alien civilization, possibly a message sent across the stars, waiting to be discovered by those who were listening. Others believe the signal might have come from a more natural, yet still enigmatic source, a rare and powerful cosmic event that we don't yet fully understand. Could it have been the result of a distant planet or star emitting unusual radiation? Or perhaps it was caused by an unknown phenomenon in the vast depths of space, a mysterious force that our current scientific tools and models are unable to identify. Over the years, a multitude of hypotheses have been suggested. Some have posited that the signal could have been the result of a satellite reflecting radio waves back to Earth, an unintended echo bouncing off a piece of human-made technology. Others suggested that the signal might have been caused by interstellar phenomena, such as the activity of a distant pulsar or a rogue comet. Each theory, while plausible in its own way, has been met with its own set of challenges and contradictions. Despite the many ideas, none have been able to conclusively explain the signal. What makes the WOW signal even more perplexing is that no similar signal has been detected since. The search to replicate or rediscover the WOW signal has become a long, fruitless pursuit. Despite advances in technology, efforts to find a repeat of the signal have been unsuccessful. The Big Ear radio telescope, once a pioneering instrument in the search for extraterrestrial signals, was decommissioned in the early 1990s. Though its contributions to science were invaluable, the search for the WOW signal continued with other radio telescopes and space-based observatories, yet the signal itself remains as unresolved as ever. In the years following the discovery, the WOW signal became famous, an icon of the human spirit of exploration and our quest to understand the cosmos. The recording of the signal, often shared online and across social media platforms, has sparked the imaginations of enthusiasts and skeptics alike. Each new analysis, each attempt to decipher its meaning, only deepens the mystery. Some have even slowed the recording down, hoping to hear hidden patterns or voices concealed within the static. One such attempt saw the signal slowed to an extreme degree, and to some listeners it seemed to say, "We lost him at 7 p.m. We've got a 161. This odd interpretation was thought by some to be a cryptic police code for stopping a suspicious vehicle. However, this theory was soon debunked when it was revealed that the slowed down signal had been altered, with the audio taken from a police radio transmission and edited to sound as though it came from space. The false connection was nothing more than a prank, but it demonstrated the lengths to which people would go to find meaning in the unexplained. At its core, the WOW signal remains one of the most mysterious and discussed events in the world of radio astronomy. Despite the absence of a definitive explanation, it continues to captivate the public imagination. At its heart, the WOW signal was a remarkable and powerful burst of radio waves, captured by a large radio antenna aimed towards the stars. This antenna, like others of its kind, was part of the radio telescope network, an array of instruments designed to detect radio waves from distant celestial objects. These telescopes come in many shapes and sizes, ranging from small observatories to massive structures that stretch across the land. One of the most interesting aspects of the WOW signal was the instrument that detected it, the Big Ear radio telescope. While the Big Ear was an impressive feat of engineering, it was not without its quirks. Unlike some of its larger, more sophisticated counterparts, the Big Ear had certain limitations that made it less capable in some respects. Though enormous, roughly the size of a football field, its design made it appear incomplete, as if a grander project had been halted midway. Despite its size, the Big Ear could not scan the entire sky at once. Instead, it moved in sync with the Earth's rotation, carefully scanning specific regions of the sky, but only for short bursts of 72 seconds at a time. This unusual pattern of observation is part of the reason why the WOW signal lasted exactly 72 seconds. When the signal was detected, it followed a very specific and predictable pattern. During the first 36 seconds, the signal grew steadily stronger, reaching a peak of intensity. Then, over the final 36 seconds, it began to fade. This gradual change in strength provided a clue that something extraordinary was taking place, something unlike the usual background noise or ordinary cosmic interference. In the years since the WOW signal was first detected, it has become a symbol of our unrelenting curiosity about the universe, a reminder that even in an age of unprecedented technological advancement, there are still mysteries that lie beyond our understanding. The WOW signal may never be fully explained, but its legacy lives on, fueling the drive to search for the answers that lie hidden in the stars. However, the discovery of the WOW signal was far from the dramatic, real-time excitement that one might expect from a science fiction film. Contrary to the cinematic portrayal in movies like Contact, where characters eagerly watch signals come in live, Dr. Iman and his team did not witness the WOW signal as it occurred. In fact, Dr. Iman noticed the sudden increase in the signal only after it had already happened. Though this may seem anticlimactic, it was just the beginning of a far more complicated and perplexing investigation. Once the signal had been recorded, the real challenge emerged. Dr. Aman's team and others in the scientific community faced a major hurdle. They couldn't find the signal again. Despite the original detection, no one could replicate it. Follow-up observations were conducted with urgency, and outreach was made to other radio telescope teams in an attempt to trace the source of the signal. Additional antennas were strategically placed in the same section of the sky where the signal had been detected, hoping to catch a second occurrence. But by the time these efforts were underway, the signal's source had mysteriously disappeared. What followed was an increasing sense of frustration. The signal's elusive nature made it clear that its detection had been something extraordinary. Despite years of trying, scientists found it impossible to reproduce the exact conditions that led to the WOW signal's initial discovery. The absence of any subsequent signals only deepened the mystery, leaving the scientific community in awe and uncertainty. One of the most fascinating aspects of the WOW signal was that it defied any conventional explanation grounded in Earth's communication technologies. The signal's frequency, 1,420 megahertz, held particular significance. This frequency is not just any ordinary radio wave. It's set aside specifically for the study of extraterrestrial signals. In fact, Earth-based communications are strictly prohibited from using this frequency. It's reserved solely for scientific research, with the aim of listening for potential signals from outer space. To make it clear, it's not merely avoided. It's deliberately safeguarded to ensure that no terrestrial noise interferes with the search for cosmic messages. The significance of 1,420 megahertz traces back to the 1950s, when a group of visionary scientists, including Bernard Oliver, Jeep Coney, and Philip Morrison, proposed a compelling theory. They believed that this frequency could be the ideal channel for extraterrestrial communication. Their reasoning was based on the fundamental role of hydrogen in the universe. Hydrogen, being the most abundant element in the cosmos, emits radiation at exactly 1,420 megahertz. The scientists hypothesized that if intelligent life existed elsewhere in the universe, they might use this frequency to communicate, much like humans might pick a common language or a universal channel to converse with one another. Given hydrogen's omnipresence across the universe, it made sense to think that other civilizations would also recognize this frequency as an optimal starting point for communication. Though this was largely speculative, the idea provided a logical foundation for the search for extraterrestrial intelligence, SETI. So when the WOW signal appeared in 1977 at exactly 1,420 megahertz, it seemed to validate this theory. It was a breakthrough moment in the search for alien life, suggesting that the signal might have originated from an intelligent civilization somewhere in the cosmos. The coincidence of the frequency was too striking to ignore. This moment of discovery reignited excitement and curiosity, as the scientific community was now faced with the tantalizing possibility that the signal had indeed been a message from an extraterrestrial source. The frequency was so important that it had been reserved specifically for this purpose, making it the perfect channel for such a profound signal. However, despite these early triumphs, efforts to track down the WOW signal again met with failure. Dr. Iman and his team poured months of effort into focusing on the same region of the sky, hoping to detect a repeat of the signal. Yet, despite their best efforts, nothing came of it. The signal remained a one-time event, as elusive as it was baffling. A decade later, in the 1980s, astronomer Robert Gray revisited the case. Armed with the latest technology, he attempted to replicate the results with new, more advanced equipment. In 1987 and again in 1989, he used the meta-array at the Oak Ridge Observatory to search for any trace of the signal. Once again, no such luck. The signal had disappeared without a trace. In the mid-1990s, interest in the WOW signal was reignited. In July 1995, Paul Schuch, the executive director of the SETI League, took another shot at solving the mystery. He used cutting-edge signal detection software alongside a 12-meter radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia. Despite the advanced tools at his disposal, the result was the same. The signal did not reappear. Determined, Robert Gray returned to the search once more in 1995 and 1996. This time, he employed an even more sensitive radio telescope, the Very Large Array, VLA, known for its superior ability to detect faint signals. Yet, despite all the improvements in technology and the persistence of the astronomers involved, the WOW signal remained elusive. It simply could not be found again. The mystery of the WOW signal remains unsolved to this day. Many scientists continue to be baffled by its sudden, unexplained appearance. What makes the WOW signal particularly remarkable is not just the fact that it was detected at the scientifically significant frequency of 1,420 megahertz, but also the fact that it came from an unknown source deep in space. Its origin could not be traced to any known earthly signal. Over the years, the WOW signal has become one of the most intriguing, unsolved mysteries in the field of astronomy, and it continues to captivate the scientific community. In 1999, two astronomers, Gray and Simon Ellen, tried once again to detect a repeat of the mysterious signal. This time, they used a 26-meter radio telescope at the University of Tasmania's Mount Pleasant Radio Observatory. Their efforts were extensive. 6 separate observation sessions were conducted, each lasting 14 hours. They searched from different nearby locations, hoping that a fresh perspective or a different vantage point might reveal the source of the signal. But despite all their hard work and the best technological advancements available at the time, the WOW signal never resurfaced. It had vanished as mysteriously as it had appeared, leaving behind only a trail of questions and a sense of wonder about what exactly had occurred that summer night in 1977. Despite the relentless pursuit of answers, astronomers never managed to detect anything that resembled the original WOW signal. Each repeated attempt only fueled doubts and further entrenched the skepticism that the signal was merely a fluke. For decades, these repeated failures reinforced the belief that the signal had been an anomaly, one of those fleeting moments that spark brief excitement only to vanish without leaving a trace. Skeptics held fast to their convictions, arguing that there was no way to explain the signal, and they cast aside its significance. For years, the WOW signal remained a subject of fascination, but with no concrete explanation emerging, the scientific community largely dismissed it as an outlier. It wasn't until 2017, almost 50 years after its first and only detection, that a potential explanation surfaced. Antonio Paris, an assistant professor of astronomy and astrophysics at St. Petersburg College in Florida, suggested that the signal might have originated from hydrogen clouds surrounding 2 comets, 266 P/Christensen and 335 P/Gibbs. Between November 27th and 16 and February 24th, 2017, nearly 200 studies were conducted. The results were surprising. As the Christensen comet approached Earth, it emitted a noise that bore a striking resemblance to the wow signal, with almost identical frequency patterns. Further investigations into other comets also showed similar findings, suggesting that comets, which release vast clouds of hydrogen stretching millions of kilometers, might create a signal similar to the wow signal. However, while this theory gained some traction, many astronomers remained skeptical. There were inconsistencies in the data, and critics pointed out that the theory didn't fully account for the lack of new signals detected in the same region of the sky. Just when it seemed that the mystery of the wow signal might fade into obscurity, something unexpected happened in 2020. A glimmer of hope emerged when Alberto Cavaliero, an amateur astronomer, made an exciting discovery while studying the region of the sky where the wow signal had first been detected. In his search, Cavaliero identified no fewer than 15 stars that could potentially be the source of the mysterious signal. Cavaliero proposed two intriguing hypotheses. First, he suggested that the signal might have come from an Earth-like exoplanet orbiting a Sun-like star. Second, he based his theory on the famous Drake equation, which postulates that such a planet could not be closer than 500 light-years from the Sun. To narrow down the possibilities, Cavaliero turned to the Gaia telescope's database, which cataloged detailed information on the properties and locations of stars in our galaxy. He focused his search on G-type and K-type stars in the Sagittarius constellation, looking for stars that met specific criteria, such as having a radius between 0.83 and 1, 15 times that of our Sun. To his surprise, one star stood out. Cataloged as 2-mass J1281982-2687, this star had a radius nearly identical to that of the Sun, with a luminosity around 0.7 times that of our Sun. This discovery was enough to reignite interest in the search for the wow signal's source. Cavaliero also identified 14 other stars in the region with similar temperatures, though they lacked sufficient data on their luminosity and size. While no major breakthroughs have emerged since then, this potential star has reinvigorated the search and sparked new hope within the scientific community. The search for the wow signal continues, but the discovery of this potential star has renewed excitement. It is possible that one day humanity will detect the elusive signal once again, or perhaps uncover an entirely new and equally mysterious signal. Such a discovery could revolutionize our understanding of the universe and the possibility of intelligent life elsewhere. However, as we search for signals from distant stars, humanity has found itself captivated not by a mysterious signal, but by an object, one that could hold the answers to one of the greatest mysteries of all. Are we alone in the universe? On October 19, 2017, astronomers across the globe were jolted out of their routine as they found themselves captivated by an unusual object that would soon be named Oumuamua, meaning messenger from afar, or scout in Hawaiian. This object, discovered in the vast expanse of space, would later become one of the most mysterious objects ever observed, and a key piece in the ongoing quest to solve Fermi's paradox. At first glance, Oumuamua appeared to be just another typical discovery, part of the daily routine of scanning the skies for new comets, asteroids, and space debris. Robotic telescopes, which now handle much of space observation, routinely spot fast-moving objects like asteroids or comets that are relatively close to Earth. On average, astronomers discover between 100 and 150 new objects every night. But Oumuamua was different. The Pan-STARRS robotic telescope in Hawaii first spotted the object, and its orbit appeared to be elongated and nearly parabolic, just like a comet. However, upon further investigation, astronomers made a startling discovery. Oumuamua's orbit was hyperbolic, meaning it was not bound by the sun's gravity. It was simply passing through our solar system at a speed that was unlike anything observed before. This was a shocking revelation. Objects like comets and asteroids, typically born in our solar system, are bound to our sun, and their orbits reflect this gravitational pull. Yet Oumuamua was different. It wasn't part of our solar system. It had come from beyond. While it's true that other stars may also have comets and asteroid belts, this was the first time we had ever witnessed an object traveling from another star system into our own. No object had ever been observed entering our solar system at such an incredible speed, and the trajectory of Oumuamua suggested that it had traveled from the direction of the constellation Lyra, more specifically, the star Vega. At first, scientists were unsure what Oumuamua was. Its unusual shape, cigar-like, about 35 meters wide and up to 200 meters long, led to some wild speculations, with many suggesting it could be an alien spaceship. But as the object continued its journey through our solar system, its behavior only deepened the mystery. Oumuamua spun erratically, with its brightness fluctuating in a way that suggested it had an unusual shape. As it passed through the inner solar system and came close to the sun, astronomers continued to track its movements. Its trajectory, combined with its incredible speed, indicated that it was not just a random object passing through, but something far more extraordinary. Despite initial excitement about the possibility of an alien spacecraft, there was no conclusive evidence to support such a claim. The object didn't emit any signals, and when astronomers sent a radio signal in its direction, they received no response. Still, as Oumuamua continued its journey away from the sun, it exhibited some perplexing behavior. It seemed to accelerate, altering its trajectory in a way that no known comet or asteroid could. Typically, objects like these accelerate due to gas and dust streaming off them, comet-like activity, but no such activity was observed in Oumuamua's case. This anomaly led many scientists to wonder if Oumuamua could be artificial in origin. Some speculated that the object's trajectory might suggest it was not merely passing through our solar system, but that our solar system had collided with it, sending it off course. This would imply that Oumuamua was on a journey of its own, perhaps originating from another star system altogether. The strange shape of the object, along with its rapid speed and erratic movements, further supported this theory. No other known object in our solar system has the same cigar-like form, making it an outlier among the millions of comets and asteroids observed to date. Some astronomers have suggested that Oumuamua may hold the key to solving Fermi's paradox. The question of why, in a universe full of billions of stars, we have yet to detect definitive evidence of extraterrestrial life. While we may never know for sure what Oumuamua is or where it came from, the mere fact that it exists challenges our understanding of the natural world. It's possible that Oumuamua is not just another comet or asteroid, but a clue, a mysterious object that defies explanation and stirs the imagination. In the search for extraterrestrial life, sometimes the most important discoveries are those that lead to more questions than answers. And while we may never have all the answers, the discovery of Oumuamua serves as a powerful reminder that the universe is full of mysteries, many of which we have yet to unravel.